Is this on? It is. Okay, so we're going to make a start. So I'm Tim O'Driscoll, for anybody I don't know, with Intel. I'm the chair of the DPDK Governing Board. So I'm just going to do a couple of opening remarks, and then we're going to start the actual presentations. So just the very boring stuff at the start. So logistics, I think obviously everybody found the location, so we don't need to go over that. The breaks are just right outside here. Lunch is in the restaurant, which is just over in that direction. So everything should be pretty straightforward to find. The back of the badge has a QR code, which will give you the schedule. People have probably seen the schedule anyway, but if you want to check it, QR code on the back of the badge. And there's a Wi-Fi access code, a Wi-Fi password on there as well. One thing for people to remember, we have a reception planned for tonight. So it's from 6 o'clock onwards. The location is there. Apparently it's about a 14, 15-minute walk. So I guess we'll meet in the lobby about 5:45. Plan to start there from 6 o'clock. Bridget and Evie were giving out drinks vouchers as people registered, so don't forget to bring those along, and hopefully everybody can make it this evening. And you'll have met one or both of the ladies already, but our two event organizers are Bridget, who's at the back there, and Evie, who is probably outside at the desk. Any questions about anything during the event, any logistical issues, anything like that, either of those people are the person to go to. Okay, so that's the kind of logistical side. One thing that Bridget and Evie did yesterday is they went shopping and they bought a few little prizes. So we're going to do a few quiz questions and see who's awake. So I thought about what types of questions to ask. There's two sections. The first section is on DPDK summits. So I guess this is checking who's been attending over the years, who's been paying attention when they have been attending. So shout out if you know the answer. And Nathan is going to run around and give out a prize to anybody who gets it right. So first question then, what year was this? This is testing people's memory. No. 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 Somewhere between you and Shobi. Yes. So this was the first time we did a DPDK summit in Dublin. So a bonus question, and this is for non-Intel people, because Intel people will have worked with this person. So non-Intel people and not former Intel people either. Who was the baker? Who was the DPDK baker? Does anybody know? Siobhan. Well done. Just right behind you there. Okay. Next question. Where is this? San Jose. Who said that? I didn't see who it was. There we go. It's the Tech Museum in San Jose. We were there in 2016. And the last question on DPDK summits. Where haven't we had a summit? Beijing. No, there was one in Beijing. No, been in Bangkok? Paris. Who said Paris? There we go. Well done. But maybe that should be next.
I was going to say yeah.
Okay. So a little bit just on project governance. So first of all, these are all the project sponsors. That's been a very stable set of companies since we set up the project under the Linux Foundation back in 2017. There have been one or two added. We haven't really had any companies drop out of the picture. These are the people who pay the bills for events like this. So it's always good to know who the project sponsors are and to recognize the contribution that they make to funding the project. In terms of governance, we have a governing board. You can see there the kinds of items that the governing board takes care of. So it's marketing, it's the lab resources, strategy, budget, any legal issues. That's mostly licensing type issues, things like that. We have a technical board who do all the techie stuff. So any technical issues, set the technical direction, approve any new projects. And then there's a couple of smaller kind of subgroups that focus more on marketing, finance, and the community lab. So that's the overall governance structure. In terms of the governing board, we have a few of them here today. So off the top of my head, Ian, who's the vice chair, is just here. Kisang, who's the treasurer, so he's the man with all the money, is over there. Nicholas is around somewhere as well. Okay, over in there. And Nathan, who's our Linux Foundation project manager. Is there anyone else I'm missing? Oh, yes, where is Wayne? Yes, there we go. Is Prasoon here? Okay, he wasn't at the dinner last night, that's all I know. So, okay, but maybe he'll make it at some stage during the day. So we have a good attendance. Tech board, probably familiar to most people, so we probably don't need to go through who's who. Any technical discussions, track down one of these guys and take the opportunity of being here in person to talk through with them in person. Okay, and then on the budget side, so this is just a very high-level summary slide. It's actually from a month or two back, but it's probably still fairly up to date, and Kisan can correct us if there are any significant changes. Just a couple of things to note on this. I mean, first of all, on the left-hand side, you'll see total budget at 714,000 and total revenue at 575. So that means we're spending more than we're taking in. Now, the project has quite a significant budget surplus that was built up largely during the COVID years. So a lot of the budget goes on summit events. Obviously, during COVID years, we couldn't have those, so that money was banked. So there's a little bit of a surplus there, which is always a good position to be in. So that's what's funding the deficit there. Obviously, long term, we need to balance that out and need to operate on a sustainable basis. But for now, the fact that we're overspending this year isn't an issue at all. In terms of the types of things that we're spending money on, so just to go through the different categories, because when you see the total numbers, the aggregate numbers there, they always look big. But then when you look at what's in them, they actually cover quite a lot of different things. So community engagement and marketing, the biggest element of that cost is the summit events like this. So we have this one here, and we have another one in Santa Clara in September. Those costs are all in that blue bucket. The other thing that's included in there, and he's not here today, is Ben Thomas, who's our LF marketing person, who helps with promoting the project, keeping DPDK in the news as much as possible. So that's the community engagement and marketing category. Development and community support, again, that sounds like a big number when you see it there. That's largely running the lab in UNH. So a big proportion of that is the lab expenses. The other thing that's in there is, at the moment, we have a tech writer working on improving the documentation. She's been doing that for a while now. So the tech writer costs are in there as well. So staff, travel, and board includes a couple of things. It includes the Linux Foundation staff that we have working on the project, so some of Nathan's costs. It also includes project funding for governing board and tech board and some other project members to travel to events like this. So that's what's there. G&A is just basically the cost of being a project under the Linux Foundation. So that's the annual cost that we pay for, basically for Linux Foundation membership. It's a percentage of the overall project budget. And legal, it's there in case we ever need to do something in that area. We haven't needed to so far, so it's zero cost at the moment. Okay, so that's the kind of governance structure. I'm going to do a couple more quiz questions. I think we have 2 more prizes left, but I have 3 questions, so I'm going to ask the questions anyway, and we'll see. So, again, test if everybody's awake. What's this, and where is it? It's what? It's in the, but what is it? It's an astronomical clock, yeah, in the Old Town Centre. So I think that's a tie. Answered half the question each. Okay. Just over here. We'll do that one. It's an appropriate prize for this particular question. Okay. So next one, everybody will know what this is. But what year was it completed? Does anybody know the exact year? Or anybody want to take a guess? We'll go with someone who can get close. Earlier than that? A little bit later than that. Hmm? No. What number did you say? Earlier or later than, I didn't hear, you said 1488. It's earlier than that. 1452. A little bit earlier than that.
1410.
That's close enough. So it's actually 1402, so you can hang on to that. And last one, a little bit more cryptic. What's this building known as? Yes. Very good. I thought that one might catch people out, but that's probably the quickest one to be answered. Okay, so that's the end of the questions. Recent progress. So I looked back at the last year or so, just looked at some of the release stats and some of the contributor and review stats just to see did anything interesting jump out. There were a couple of interesting things. So I looked at contributing companies and organizations, and the top 3 are what the top 3 always are. It's Intel, NVIDIA, Marvell, no surprises there. But when you look at kind of contributing companies and organizations, number 4 was a surprise to me. So does anybody know what, and there's no prize for this, does anybody know what number 4 was? No. Stephen. Network plumber. Stephen Heminger. So when you look at that, and to me that was amazing. When you look at the top contributing organizations and companies, number 4 is an individual. So we used to, in some of these summits previously, do some community awards. And it was only when I saw this that I thought that's something that we should reinstitute, because that's an incredible achievement. And the rest of the top 10 are pretty much as you'd expect, the usual suspects. So then I looked at reviewers, and Thomas, when he sends out his release email, always lists the non-PMD reviews. So that's what I did. I totted those up for 2403 to 2503. So anybody guess who the top reviewer was? Bruce? No. Morton. I think, so well done, Morton. Bruce is only number 3. I think I have a recollection of doing these numbers before and Bruce was top, so you're slipping. You're headed in the wrong direction, Bruce. But this is important because, you know, everybody is concerned about their own patches. These are people who are reviewing other people's patches. So it's not their job to implement that change. It's not their job to get it in, but they're taking the time and the effort to review and act other people's patches. So it's an important thing. And UNH Community Lab, we have Patrick here. So anybody with any questions on the lab should take the opportunity to get some time with Patrick. We need to make sure, I mean, the lab is doing a great job. You can see from the stats there. We had a meeting between the governing board and the tech board last night, and everybody was very complimentary about the work that's being done in the lab, the benefits that it gives, the fact that it helps catch a lot of issues much earlier than we would otherwise do so. But if you have any thoughts on other things that we could or should be running in the lab to try to catch even more issues, Patrick is the first point of contact. If there's any cost implication, we can work that through the governing board. But we should definitely try and build on this as much as we can, maximize the benefits that we get from it. Okay, this is just an updated view of the hardware in the lab itself. So then, yeah, very final thing. We have another DPDK summit in Santa Clara in September, hosted at the Intel campus. I think the registration link is live now. Is it, Nathan? It is. Yeah. So people can start to make plans, register. I think there's a block booking of hotel rooms as well available. So we'd encourage as many people as possible to attend.
We should have a CFP slide too with the QR code there and the
yes. So yeah. No, we'll do that. But yeah, the details will all be, if they're not already, they will all be up on the website shortly. And the only other thing to note about this is that the project DPDK will be 15 years old at this time. So we'll try and build in some kind of recognition, celebration of the 15-year milestone for DPDK. And that's it. So just thank you all for coming. Hope you enjoy the summit. And like I said, take the opportunity to talk to people in person, do a bit of networking, maximize the fact that you've gone to the trouble of traveling and being here in person. It's good to take advantage of that. It's good to connect with people like Patrick for the lab and lots of others that you wouldn't necessarily encounter on a day-to-day basis. So that's it for me. I think the next presentation, I believe, is Konstantin and Francisco from Huawei talking about SO ring.
Okay, good morning everyone. First, let us introduce ourselves. My name is Konstantin.
I'm Francesco.
Hey guys, so today we're going to talk about our latest contribution to DPDK, about what we name it stage ordered ring, about its basic concept, internal design, and possible use cases. Yeah, I will start and then Francesco will continue. Okay, so at first a bit about motivation. So as you all probably know, the most common way to distribute packets across multiple threads in DPDK is to use hardware, right? It could be either RSS, offload director, or something in that area. Well, it worked quite well, but in some situations, like elephant flow, number of packets per flow can exceed CPU capabilities. And in such cases, we do need to another way to distribute packets and distribute work among multiple workers. Usually that comes with extra requirement to preserve ingress packet order per flow. This thing is, and this problem is not new, right? And inside the DPDK, we do have event-dev framework to tackle that. Event-dev framework provides three types of queuing. It's parallel, ordered, and atomics. In majority of cases, it works pretty well and covers all the needs. But again, not always, right? There are some situations where, by different reasons, technical or non-technical, it's not feasible to use event-dev framework. Let's say hardware-based PMD, they do usually provide good performance, right? But for that, you require a particular hardware model, which is not always the case. Another thing is software-based implementations. They do exist, they do work, but they do have their own restrictions in applications. Some of them require extra cores to do actual packet scheduling. Another one would work only with DPDK cores. Not all of them do meet our performance expectations, right? So with all this in mind, we come up with our own set of requirements, what we want to have, right? So we want to have an ordered queued abstraction that is hardware agnostic, which means pure software implementation. It has to be as fast and lightweight as possible. Generic API that could be easily adoptable by existing and new DPDK products. And it should support both multi-threading and multi-process DPDK deployment models. Actually, can you hear me okay? Because I'm too far from microphone. Okay, yeah. Okay. Okay, yeah, okay. Thank you. Okay, so keeping all that in mind, we come up with what we name at stage ordered ring, aka ring. So what is it? It is a software subtraction for ordered queues with multiple processing stage. You can look at it as sort of an extension to RT ring. It has similar API. It shares many design concepts, and it even reuses parts of RT ring code. Okay, so its main properties, it's still a circular ring buffer with fixed size objects. It has producer, consumer, plus multiple processing stage in between. Usually objects remain in the same ring while moving from one stage to another. That helps in terms of preserving initial package order, plus to avoid extra copying in between. Each state, same as producer and consumer, can be served by multiple or single thread. It's up to the user to decide. For producer and consumer, all conventional RT ring synchronization mode are supported, and number of stage, size, and number of objects in the ring are configurable at initialization time. Now, I have to say that this concept of circular buffer with multiple stage is not new in DPDK. From best of my knowledge, it was first introduced with OPDL event-dev PMD. Soaring and OPDL, they do share a lot of concepts like multiple stage, head and tail position, moving head and tail to obtain elements. The main difference is how release operation is done. I will probably cover that in next few slides. Okay, so let's have a brief look at Suricata API. From my perspective, it's very simple and straightforward. On the left-hand side, you can see the pseudocode for control path usage and API usage, and on the right-hand side for data path. So, yeah, as usual, user has to start with filling initialization parameters, then call get mem size, which in return will tell how much memory this Suricata will need. After that, it's user responsibility to allocate required chunk of memory and call RT Suricata init. After that point, serialization is finished and Suricata instance is ready to use. Data path API. Data path consists of 4 main functions. It's enqueue, dequeue, acquire, and release. Again, enqueue and dequeue works exactly the same as conventional RT rings counterparts. Acquire and release, that's basically for multiple stage processing. After acquire returns, thread that calls it can safely assume that obtained objects, that it has exclusive possession on obtained objects until it calls release for them. 2 important things to note. First one, the thread has to call release for exactly same amount of objects as was acquired before. And second one, all data plane functions pass along not only the object itself, but associated metadata. Let's say on this example, we do have an object of 8 bytes, usual pointer size, right? And we also have associated 4 bytes metadata object. So why to do such separation? It could be useful for performance. For example, user may want to separate a packet processing state in this metadata. Then it can check and update the status value even without touching the actual objects, which is useful for some bulk operations, probably for using SIMD operations and so on. Okay, let's look a bit at internals part. So internally, we do have usual producer and consumer head-tail structures, plus we have an array of stage structs with sort of enhanced head and tail values inside. Also, we do have an array of states, 1 state per element in the ring. This is completely internal structure and is used by release and acquire operations. So how it works? Enqueue and dequeue, again, it works exactly the same as with RT ring. We do move head, then we copy in or out obtained elements, and then we finally call update tail. Acquire also starts with move head for its head value, for its stage head value. But then it does 2 extra things. First one, it updates state element at obtained head position to mark this group of elements as in use. Also, it returns to the user an F token. F token is a 32-bit value which encodes information that is necessary for release operation. It contains obtained head position plus stage index. Okay, at release at its turn, deduces from F token old head position and stage index. Then it again updates state element on old head position to mark this group of elements as released. And then it calls a finalize function. Finalize, it's internal function that main purpose is to do actual tail update. So what it starts with, it tries to grab exclusive write log on tail value. It's basically sort of exclusive mutex log, right? If it fails, it simply returns and let other threads to do finalize for it. If it on success, it scans through state array, starting from stage tail up to head position. If the element is in release state, it updates the state to mark it unused again and move head position forward. It will stop in two situations. First, when we reach the head. Second, when we encounter an element in non-release state, then we have to stop. Yeah, basically it's, I tried to explain it in pictures, and as you can see, we do have finalize operation, and even we do have released element after non-released element, we have to stop here. So this separation is quite useful in terms of, because of this shared state and exclusive log, now we could do update tail operation from multiple places. Of course, we do it from current stage release, but we also can and do it from next stage acquire operation. And even for the last stage, we do it from consumers dequeue operation. That helps in terms of now we don't have to spin on tail, update tail, we don't have to spin on tail value as OPDL and usual RT ring implementation do. Okay, so next slide. Okay, thank you. Okay, now let's talk a bit about benchmarking. So to see how fast Sarin can go, we took our conventional L3 forward application, right? As you might know, L3 forward can run in two modes, as a run to completion or in the pipeline mode. For pipeline mode, you do need to use event dev. And the pipeline mode, it's very simple. It contains only three stages. Stage 1 of pre-process is where we receive our packets, we determine packet types, and we put them into working queues. Stage 2, which is actual processing, that stage could be done in parallel. So worker thread takes packet from the queue, do actual process, which is ICL table lookup in this case, update layer 2 and layer 3 headers, and put packets back together with the processing status, either accept, drop, or route to particular network port. Stage 3, which is again single-threaded, is post-process. So IO thread dequeues packet from and their status from the queue, and either transmit or drop them. So to do our own benchmark, we enhanced L3 forward application a bit. You can see a link to this patch on the top. So first of all, we added support for ICL mode in event dev case. And second, we introduced two new modes. We named them ordered worker queue and unordered worker queue. Ordered worker queue implement exactly the same pipeline, but using stage ordered ring. Unordered working queue doing exactly the same again, but now with two RT rings, with conventional RT rings. Obviously, unordered working queue doesn't provide any ordering guarantees, but we do use it as performance comparison with between SO ring and RT ring. Thank you. Okay, so let's look at what we get here. Right, so on the right hand, on the left hand side, there is L3 forward running in ACL mode over traffic that contains 10,000 evenly distributed flows. On the right-hand side, it's exactly the same application with exactly the same set of rules, but now all traffic belongs to one elephant flow. So yeah, few takeaways from it. First of all, for evenly distributed traffic, run to completion is still the fastest one. But it doesn't perform well for elephant flow, as you probably expect, right? For ordered pipeline, it performs nearly the same for both cases, right? So, and as you can see, there is, it scales till some limit. After that, it becomes really flat, and spawning extra working thread doesn't make any difference, right? This new limitation is obviously the maximum performance that I/O thread can get. So obviously that's the cost of pre-processing and post-processing stage. To improve situation, we need to make it as fast as possible. But anyway, sooner or later we will hit this limitation. Right? I forgot to mention that in both cases we have just one I/O thread. All other cores were running worker threads. Another good thing for us that for all tests we run, RT ring and RT SO ring implementations provide nearly identical performance number, which I take as a good success for us, right? Okay, a bit more about performance analysis, right? So let's first look at the picture on the left. Right, you can see two lines. One is for run to completion, another for ordered pipeline, and again, it's running the same as the forward application with exactly the same set of rules. And as you can see, as percentage of packets that belong to elephant flow start to grow, run to completion performance start to degrade. I marked this gap in red, right? And that's basically the performance that user has to sacrifice when he decides to switch from run to completion to ordered working queue mode. And obviously, sacrificing performance is not a good thing. So we thought what we could do to improve this situation, and what we come up with is what we name a hybrid approach, a hybrid mode. In this mode, each thread can combine both I/O thread and worker thread behavior depending on the traffic, on the current traffic pattern. To put it simple, when there are a lot of packets in its worker queue, thread do process packets from its own worker queue itself. When it becomes idle, there is no more packets in RX queues, it starts to behave more like a worker thread. It means that it starts to process packets from other thread queues. And you can see that helps quite a bit. We managed to obtain reasonably good performance numbers for it. It's a yellow line, so we have reasonably good performance, I would say, for both situations, for evenly and unevenly distributed traffic. Okay, and this is last slide from my part of presentation. So current status and what next. First of all, SO ring is upstream to dpdk.org. It's part of official DPDK release starting from 2503. What about future plan, future use cases? One thing that we're looking at, and if the time permits, we would like to enhance our, by our, I mean DPDK software-based crypto PMDs and allow them to work in asynchronous mode transparently. So for that, we plan to use SO ring as a queuing mechanism for crypto dev queues, right? And that hopefully allows us to distribute work computationally extensive part of work among multiple cores while still preserving the order. Again, we hope that Soring will become widely adopted within the DPDK and people would come up with new exciting use cases. Okay, that's it from my part, and now I pass microphone to Francesco and let him continue.
Thank you, Konstantin. So, hi, Francesco. I'm part of the Huawei Cloud Data Plane engineering team in Dublin. So I'm just going to showcase a little bit a POC that we developed on top of an actual Huawei appliance that's used in production, not the POC. So what's the current design? The current design of this is mostly an ACL and connection tracking appliance. It's DPDK based, it's doing multi-threaded symmetric packet processing, and it also follows a run to completion model. So in these appliance, user can create custom plugins, they can stack them up, and they are dynamically loaded at startup. And so the components runs from start to end on each batch of packets, and that are queued from the hardware queues. So the appliance assigns one queue per NIC to each IO thread, so it's pretty much standard on that side. And so the objective we wanted to achieve was to enhance the appliance ACL lookup performance in presence of uneven traffic, so when we have elephant flows. Since with RSS, as Konstantin already highlighted, by default all packets are going to hit a single core. We can't really take advantage of the parallelism of the appliance in these cases. So there was a big challenge here because this is brownfield development. This was legacy code, so we didn't want to change too much the pre-existing design. So to better understand how we did this development, I'm going to go briefly on the ACL component structure of that legacy code. So this is the design for round to completion. The key aspect of the execution model is that filter table lookup. As per IP tables, we have row table and filter table lookups. And the most expensive one is the filter table lookup, because they implemented a custom classification function there. So we decided this was going to be our candidate for asynchronous parallelization. That was the guy that we could take off from the main pipeline and offload to other threads. So we also, to clarify the process, we define a set of actions that go before and after the filter table lookup. So as I told you, row table lookup, connection tracking lookup session are done before, and then in case this was a new flow, we're going to have session create after the lookup, or an update in case the session already existed. So an important aspect of parallelizing this type of workflow is that you want to keep packet order in flow, especially for stateful stuff. So we decided to leverage SRing. That was a very good use case for SRing. So these graphs, very similar to the previous one, but just show us how it looks like when we introduce asynchronous processing in the filter table lookup. We need a new node into the graph to resume the post lookup execution once packets are dequeued from the ring. The asynchronous filter table lookup returns an action in the packet metadata, and then we take some decision after that before even resuming the rest of the execution. So just one thing, if we do connection tracking, and this is not the first packet of the flow, so we already did that asynchronous lookup, then we're not going to reinject the packets in the ring. We're just going to keep processing them synchronously. So this is the design, the new design of the appliance. We had to refactor quite a bit the code to make it more modular, to basically match that graph I showed you before. The idea is that the IO threads still receive a batch of packets from the NIC, performs all the pre-lookup operations, and then enqueue the packets in the SRing. Other threads, for example, like the worker thread pool there on the top right, will then do acquire release, do the filter table lookup asynchronously, and then release the packets in the ring. Independently on when that happens, the run to completion, the IO thread, will dequeue packets after enqueuing them and keep processing on the main component pipeline. So the IO threads, in future developments, we really want these worker threads to be able to process anything, not just ACLs. So the idea is to keep them generic at some point, and the appliance to be able to process them, to process any other type of computation. So following also what Konstantin already presented, the hybrid mode, that was really interesting, right? So that asynchronous stage doesn't necessarily need to be inside the worker thread. It can be into other IO threads that are idling. So simply enough, when there's just a single thread, like in that case, that is actually processing packets from the NIC, the other threads will be able to detect that and say, okay, I don't have any work, let's check if in the other threads or ring there's some packets to process. If there's any, they're going to take it on their own. There's many definitions of idleness, but let's assume that's just that, right? We don't have any packet in our NIC. Nevertheless, we cannot rely exclusively on other threads to do our ACL work, otherwise we get stuck. So when all the cores are under load, the IO threads will process the packets from their own threads. We did a very similar performance assessment as per the layer 3 forwarding POC on these other POC, and the performance is very much similar, right? So on the left we have the behavior of the system when we have evenly spread traffic. So all our cores are busy, all our cores are processing packets, and what happens there is that round to completion outperforms our system. That's expected. So hybrid mode is really close actually to round to completion. The gap is very small, while worker threads do get some penalty at some point because they're limited by the IO thread speed and by the fact that we're always enqueuing packets in the ring and process them on other cores, which induces some performance penalties. What we really wanted to look at that's the plot on the right, which is when we have unevenly spread traffic. In this case, we have only 2 flows that concentrate 90% of the traffic, and then 10,000 flows that concentrate just 10% of the traffic. So what happens basically there is that round to completion, which is the blue line, it's just going to scale up until the 2 flows are spread across different threads, and then it's going to flatline. So it doesn't change when you keep adding parallelism to the system. But that's not the case when we use SO ring, and when we use especially hybrid mode, which is able to provide basically the same performance as worker thread, a little bit better, but we basically without any additional cost. We're not spawning any worker threads, any additional threads. So we were very happy with the results of hybrid mode. Just to wrap it up very quickly. We were happy with the redesign of our POC. We improved uneven traffic without a complete data plane redesign for our production legacy code. We leveraged SRing to do that. And we're especially happy about hybrid mode performance because we were able to improve up to almost 3 times for uneven traffic. And the performance penalty induced compared to RTC on evenly spread traffic, it's between 5 to 20%. So 20%, it's considerable. So just keep in mind what's your use case, right? So if you're always going to have small flows and you're always going to have evenly spread traffic across all your cores, probably it's better to keep RTC. But if you are behind some very heavy, bulky applications that are going to concentrate just a few flows, transmitting a lot of data, the improvement is quite worth it. So I'm just going to leave the word to Konstantin for some final remarks. Thank you very much.
Okay, thank you, Francesca. And here is our last slide. We would like to say thank you to everyone who helped us. With that, first of all, we would like to say thank you to all our team members who put a great effort into it and make it happen. Also, we would like to say thank you to all DPDK community members who helped us with it in code reviews, in providing comments and so on, and especially for people from multiple companies who run soaring tests on their custom hardware. As you can imagine, in our lab we don't have a big variety of hardware systems, so this help was really invaluable for us. So thank you all. That's it.
Any questions at all, the gentleman?
So you said that, Konstantin, hello. You said that in the first slide that there's a limitation that you can use OPDL only in DPDKL cores. So is it so do you imply that the soaring can be used in like non-DPDKL cores? And does it suit better for event dev pipeline, or can I use it differently?
Well, right now, okay, first of all, yes, from best of my knowledge with the PDL, you are stuck with the PDKL cores, right? So with Soaring, you don't have such limitation. You can use any thread because it doesn't use RTL core ID inside. Right now, they are completely separate implementations, which is probably not the best way, but yeah, here we go, right? So would it somehow converge in future? At that point, I don't know. I would like to, but yeah. Did I answer your question? Yeah. Okay, yeah, as I said, we looked at event dev, and yeah, in our case, we decided it's not probably the best choice. First, because of this technical stuff. Second, because it's not easy to convince people that do have a legacy code to redesign the application completely. So we come up with this thing which is light and small. Yeah.
How do IP fragments fit into this new type of pipeline?
Sorry?
IP fragments.
Fragmentation. Well, I thought it's orthogonal. Can you probably explain what the problems you
So if you
foresee?
if you get some packets and some of them are IP fragments, so they don't have the TCP, so the TCP or UDP port numbers and cannot be directly related to a flow.
Yeah.
How do you handle those fragments with this pipeline?
Okay, so yeah, this is a known problem. The best way I know to deal with it is just to make all packets to arrive on one core and distribute them in software. Another way is you can still do RSS on fragmented packets, but in that case you probably want to do RSS only on IP source and destination. You can do that, and that in this case all fragments for the same flow will still arrive to the same queue, right? And yeah, that's the only thing I can come up with straight away.
Okay, thank you.
Any other questions for?
Yeah, hi, Nitin Saxena from Marvel. I have, first of all, nice presentation. I have two questions. One is, can the worker thread participate in more than one soaring RT-ring? That's the question.
Yes, it can. Yeah, I didn't put much attention on that part, but yeah, on that picture I tried to show that one thread can process different stages and act as both consumer and producer, or as worker for multiple stages. Yeah, it is possible. Yeah.
Okay. I have a follow-up question that what is the motivation of using hybrid model? Because if you use RSS, you will lose the packet latency, and if you use the event dev, then there will impact on the throughput. So what is the motivation of using hybrid model?
Well, motivation is to avoid this. Motivation is to avoid this gap, basically, right, for hybrid mode, because usually you don't know what sort of traffic will come up in the next few seconds, right? So it's completely undeterministic, right? So it could be elephant flow, one elephant flow. It could be several flows. It could be a lot of small flows. So in our system, we want reasonably good performance for all possible cases, right? So, yeah, of course, we can't make it perfect for all cases, but we try to make it reasonably good for all cases. That's why this hybrid, the idea of hybrid mode is to avoid this, avoid this gap, which I mark it in red. So, yeah, because obviously, if let's say if you have only two modes, run to completion and worker queue, right? You have to decide at startup. Okay, I do expect elephant flows traffic, so I have to sacrifice performance in case of evenly distributed traffic, right? And this gap, it could be quite big, right? And this is not always what people like to do, right? Because nobody likes to keep cycles on the table, right? So that's the motivation for hybrid mode.
So is there a practical use case you're trying to use with hybrid model?
Yeah, we used it for the part that Francesca presented. For our, we do have a production system in our proof of concept. We do use both modes. We use hybrid mode and we use worker thread mode, yeah.
Okay, thanks.
And a question from David, I believe. Where's David?
Yeah, sorry, just a simple question. You mentioned that you had an example updated with SO-ring, but I cannot see it much.
L3 forward?
Yeah.
Yeah,
there
is a patch. It lies there forever for two reasons. First of, I do have a link on one of the slides. Let me show it. Yeah, just a second. Yeah, here on the top. Well, it hangs around for two reasons. First of all, I don't have enough time to structure it properly because it is one bulk and I need to split it into multiple small patches. And second one, there was no real interest in the community to enhance L3 forward for this thing. I'm a bit conscious here because usually it's a lot of resistance from community members when someone, and me too actually, yeah, when someone tries to modify L3 forward application, because every company uses it for performance numbers
as
and
a reference,
so, yeah. But yeah, if I'll try to, but no hard promises to make it a proper patch.
We need a good example, I would say, of a use of SO-ring.
Yeah,
the unit tests are not enough from a point of view. The documentation is good, but a real example would help.
Okay, point taken, yeah.
Any other additional questions for Francesco or Konstantin? If not, I think we're good. Thanks very much, gentlemen.
Okay, thank you guys.
Okay, the next talk is from Ori Kam of NVIDIA. The subject is enhancing multi-process DPDK applications with external queues for seamless offboarding.
Thanks. Thank you very much. Bye.
I can't see this representation. Representation disappeared. Yeah, I don't know. I don't know where the representation went. It was there. Let's see. Here it is. And then, I don't know.
It's going to be a color space issue.
Do we know something about it?
Can you go to the display settings?
Sure.
Or it's just building the anticipation.
Yeah. Luckily, it's a short one, so. Where did it go? Sorry, it went somewhere. Maybe I'm missing something. It was there. And of course it's incorrect. Okay, sorry for that. Today I'm going to have a short talk about how we can enhance DPDK application using external queues for seamless offloading. A few words about myself. My name is Suricata. I'm a staff engineer at NVIDIA. I have over 20 years of experience in software development and 8 years in DPDK, and I'm the RT flow maintainer. The problem is that we have sometimes application that works very well, but when we deploy it in other systems, in other environments, basically it doesn't perform so well. The reason for that is, for example, now in the new environment, the packets are arriving encrypted or tunneled. Sometimes in the new environment, not possible. Sometimes it's not our application to change, and sometimes to do so will take time and we need a solution right away. DPDK supports basically the multiprocess model, but the multiprocess model in DPDK basically means that we have one application with number of processes which can share resources, but that's it. And we have the ability in DPDK to run different applications. Each application is a standalone application. In this case, we don't have any sharing resources, and we have no way to communicate between those two applications except normal inter-process communication mechanisms. So let's look at a simple example. We have an application A, which basically used for caching video packets. It works very well, it has its own logic, and everything is okay. Now we're moving to a new environment where the packets are encrypted or tunneled. Basically, in this scenario, the application stops working for us. It cannot do its work, so we need to update it. Let's assume for 1 second that we cannot update it from the reason that it's not our application or it will take too much time to update it currently. So our only solution is basically saying, okay, let's create a new application, a DPDK application, that will receive the packets, will modify them, decrypt them, decap them, and only then send the packets to the original application. The only way this can be done today is using the inter-process mechanism. By the way, Lucas, here somewhere, basically presented a talk about it a few years ago, where before Suricata moved to DPDK, he simply created a new application to filter out the irrelevant traffic and to pass to Suricata only the relevant information it needed. And he got huge benefits from that. So, taking this into account, what can we do to help? So the solution that I'm suggesting is basically registering external queues. External queues basically means that application A defines the queues, is the only one who actually uses those queues, but it can pass this information to a different DPDK application, and this application basically can offload traffic and basically direct traffic directly to the original application. Basically, by implementing this logic, we can split the infrastructure between the core logic and the environment and what are the packets, and introduce new offloads and other mechanisms. Let's look at the example. We create one application, the original app, basically, and register the queues in application B. And application B basically gets the traffic, modified accordingly, offloads the traffic, and then application A, from his point of view, nothing is changed. If we want to look at it visually, basically, we have application A receive the traffic directly from the NIC. Now the packet format is changing, new environment. So we introduce application B that actually decrypts or filter out irrelevant traffic. Application B now gets the traffic, and currently the only way for it to pass the data is basically use inter-process communication to application A, which is suboptimal. What can we do is simply make application B offload the relevant rule, but in the offload mentioned that the active queues that the traffic should be sent to is basically application A. So in this case, application B doesn't take too much CPU, it's basically just did the offload. Application A works as expected, it doesn't know the environment changes, and from his point of view, everything is working. And basically, even if we just wanted to add offloads, we don't need to update the application A. Use cases. IPsec offload for gateway. For example, we have a gateway. Now we need to support IPsec, so we can add the IPsec as a different application until we modify the gateway. Telemetry. Actually, we want to measure traffic before arriving to the application, so we can intercept that traffic in the middle. AI inference. Again, there are different kinds of packets, and we want to send the inference packet very quickly to different queues as fast as possible. P4 control plane. Basically, by definition, P4, there is two different applications. One application handles the offloading, and a different application basically handles the traffic itself. So it's built it's by definition, and that's about it. Thank you.
It was just a lightning talk. Any questions for Ori at all? We've got a couple.
Could you pull up again just the basic diagram showing the operation?
Sure.
So
Sorry.
Am I right in saying the basic idea here is you take the packets, send them back to the network card, and the network card then forwards them to the correct queue using filtering rules? Is that more or less it, yeah?
Yes, we can do the offloading. Yes, basically, we can, in this drawing, I didn't show it, but basically if you look at application B, when you arrive, first you got the packet. First packet, of course, in order to initiate the offload and anything, assuming that you got the first packet, then application B basically will need to send back the packets, and using loopback, application A will receive everything as starting point and everything.
Okay. So does this, I suppose the obvious downside here, is it not, it's using 3 times the PCI bandwidth that it was before, right? Because the packets all have to come in, go out, and come in again, right?
Yes and no, because we are talking only the first packet, right?
Okay.
If you're assuming offloading, and that's the idea, it's the idea that the packet will, not all the packets will be handled by application B. If all the packets are handled by application B, then you're correct, the latency.
Okay, so if your hardware supports an offload for the particular operation you're trying to prepend, it works. If it doesn't, then you're basically...
Then, there is no way to do so, yes.
Okay, thanks. That's clear now.
We have time for one more question.
Hi, Lucas here. I just wanted to ask, is this also relying on the primary and secondary process model? Or
No, it's totally different. That's the idea. To distinguish this completely between the original application and the new application. That basically, the only thing that we need to do to change the original application is just a new function to register its queues. That's it. We don't know anything about it. It's a totally different application. So any issues with one of the applications doesn't affect the other. Totally distinct applications.
Okay, but still the application B needs to, let's say, configure the NIC to prepare kind of the NIC for the application A to attach to the NIC, right?
No, because it basically is application B configures the NIC. The only thing that it needs to configure is, instead of configuring its own queues, is configuring the queues that was supplied to him by the other mechanism. So the queues themselves, even now application A configures queues, expects to get data on those queues, right? So now, instead of getting those data on these queues, it's getting the data, but he also set notification to application B, those are the queues I created. So you can please send the traffic to there instead to yourself. That's the idea.
Okay, thank you.
Sorry? Basically, it can be application A can be any of it can be also kernel, but assuming the outdoor support. For example, in our case in NVIDIA, we sometimes use application A as kernel or some other application that is not related. Since in the hardware itself, application A creates the queues. So as long as application A created hardware queues, we can point traffic. So that's the idea. In DPDK, it's more common to create the queues in the hardware. So it's a good example for DPDK. Yes.
Can we use a VF-based model here, like one VF assigned to application B, and then it gets the packets and then sends it to the NIC, and there is an embedded switch which will again use another VF to send it to application A?
Yes, but in this specific talk that I talked about, it's more like in the same VM because you want to change a specific. Theoretically, this application B, we can create a router between applications, for example, for the AI packets and everything, and we can have application A and application C. But using, I think there is another talk after my talk that basically allows it, and that's the service chaining between different VMs and everything. This can be used, but usually due to security, you don't want to expose the queues between 2 different VMs. But there is other mechanism to do that, and I think Ronnie has a presentation about it if I don't have a mistake.
Okay, thanks.
We had another question from Jaron Jacob over here.
By DPDK primitives, how to register a queue, meaning that's not there right now?
Sorry? No, it's not there yet.
Okay.
It's a simple API. I wanted to suggest it and then implement it, basically. It's a thought that I had a long time, and I said I'll display it.
Okay, any more questions, guys?
Maybe just a small question. Do you already have, sorry, I'll repeat it. Do you already have an example of this online?
No, we have examples. We are using such a approach. Currently, it's used as a private API in DPDK. MLX5 supports this. There is a way to register this queue. It's a private API, so we didn't expose it yet to the community. It is in the PMD documentations, but I need to find the use cases that they're using it, but currently they're using it in different application. Application A is not a DPDK application, it's a different application.
Okay.
It's a doc application currently, as far as I know.
Okay, I see. Yeah, thank you.
Sure.
Okay, any more questions, guys? No? Okay, then thank you, Ori.
Thank you.
Okay, guys, now then we have a break, right? It's until 10:40, if I'm not mistaken. Yeah, so, yeah. You have some free time to socialize and probably have some coffee, and that's it. Okay, thank you.
Sorry to mean to usurp that. I love how many questions we're getting. It's great. A lot of participation. That's awesome. Good presentation, too. Yeah.
It will change.
Yeah, it's still people that are tired, you know? So.
Okay. It's a well, off. Yeah, it's here.
I don't know.
I think someone was rolling outside of their suitcase. Do you think that there's anyone who would be interested to? Yeah, we have the city. Where are you based? The company is Israel. But we have
Are these centers in the US also?
I think so. I mean, we're in the team. We develop cloud software. So we're not the hardware team. The hardware team, I think, big part is also in Israel.
Yes.
From Huawei. No. Yeah, exactly.
But your team is not running on the Toga Silicon.
No.
It's
It's general purpose. So this might be interesting. Yeah, we're starting to mess around with other hardware. It's not general purpose. Yeah,
exactly. Because we have ARM also.
You do, yeah. Nice.
64 core Neoverse. You know the Neoverse from Constantine? It's a very strong powerful ARM core. You guys have a post of your application to ARM already?
No, not yet. Just not yet. We just got the server like 2 weeks ago. Cool. You should talk with Constantine because because the project now is going to move to new phases. We're going to have a few other things to add, and I'm moving to something else. But maybe it's interesting and testing on other things. Yeah.
We're engineering, not marketing.
Yeah, no.
It's interesting.
Yeah. Sure. Let's go check through.
But I don't know how it comes out of the recording. It's just on the speakers it was on and off, and fading.
Pretty good presentation. So the sound that I was referencing, he was saying, is the cart.
So maybe we'll keep the door closed. Ethan, Hello. Thank you. Can you start?
Yes.
Hello. Very good morning, good afternoon, and good evening to everyone present here. I hope you are having a wonderful day today. I am Dhanalakshmi Saravanan, Director, Security Software at Marvel Technology. I lead crypto, payment, and compliance team. My co-speaker is Venkana Rachakunta. This is our very first DPDK summit, hoping to continue our DPDK journey from here on. In this session, we will be walking you through the MLDSA processing in DPDK. Before we dive into the topic, we will glance over the history of quantum computers, its impact on the classical computer, need of PQC, and NIST PQC migration plan. Then we will move on to that MLDSA algorithm, TLS 1.3 handshake, code and firmware signing with and without MLDSA. Then MLDSA in DPDK, the current project status, and finally we will leave the time for the Q&A session. As we all know that classical computer works on the bits. It represents either the two state 1 or 0. Even if we combine the bits together, each bit is represented independently. Unlike the classical computer, quantum computer works on the qubit. Each qubit can hold the many states using the concept superposition. Also, the multiple qubits can combine states together using the concept entanglement interference. Due to these multiple states on the qubits, the error rate during the computation in the quantum computer is much higher than that of the classical computer. The power of bits in the classical computer is linearly proportionate to the number of bits. For example, 3 bits will represent the 8 combination in the classical computers. Whereas 3 qubits represent multiple combination in the quantum computer due to its superposition capability. With this concept, we can achieve many breakthroughs into the real-time industry problem like pharma, space, and the agriculture. Let me walk you through the journey of the development of the quantum computers. The first 2-qubit quantum computer is developed during 1998. Since then, this domain has seen tremendous growth. Now the world's largest quantum computer featuring 1121 qubits. The major milestone achieved in the quantum computer when quantum supremacy has been achieved for the real-time problems. Now major companies like IBM, Google, and Microsoft have invested in quantum computing and recently unveiled the quantum processor like Willow and Majorana 1. Mathematicians Shor and the Grover have proved that in the mid-90s that RSA and AES can be broken. Even with the world's fastest supercomputer, it will take trillions of years to break the RSA 2K. So it's a great news. We can use RSA for many more years without any problem. Wait. RSA and ECC using the factoring large integers and the discrete logarithm. This can be easily solved using the quantum computers. The two algorithms are vulnerable to the quantum threats, even though AES and SHA also have the quantum threat and it is not as vulnerable as RSA and ECC. We have the time for that AES and SHA replacement. Data harvest is the major threat to the sensitive data. What is data harvest? Harvest now and decrypt later is the threat actor to gather the sensitive information and store it now. Once the quantum computer is available, decrypt later. To overcome the losing of the confidential data like government secrets, bank details like PAN or the PIN details, health card records, or the personal identification information, or corporate intellectual property, we must act now to protect our data. So what do we do now? We have seen the impact of the quantum threads. How can we overcome the quantum threads in the classical computer? Here comes the PQC. Post-quantum cryptography, generally referred as the PQC, is a set of cryptographic algorithm standard to overcome the potential attacks from quantum computers. It is also known as the quantum proof, quantum safe, or quantum resistance algorithm. Unlike discrete logarithm or the factoring large integers used into the RSA and ECC, this algorithm uses the lattice, hash, code, multivariate polynomial, and elliptic-curve isogeny-based mathematics. Recently, isogeny-based PQC algorithms have been removed from the selected PQC list as it has been vulnerable for the key recovery threats. National Institute of Standards and Technology, called NIST, has started working on defining the standard since 2016 for the PQC. It has received the 82 submissions. In that, it has selected 7 candidates and 8 alternative candidates. In that, 3 has been finalized for the signature generation and verification and key exchange algorithms. 2 more algorithms are in the public review now. As these algorithms work on large key size and the signature sizes, NIST called for the additional signature sizes with lesser key size and the signature sizes. Upon the various rounds of the selection process, MLDSA, MLChem, and SLH-DSA has been finalized by the NIST last year for the deployment. 2 more algorithms like Falcon and HQC has been in the final public review and will be finalized soon. Here the MLChem and the HQC are the key exchange algorithm, whereas MLDSA, SLH-DSA, and Falcon are used for the digital signature. Apart from these algorithms, LMS and XMSS algorithm for selected for the code signing. The deadline has been defined by the various standard organizations around the world to deploy the PQC by 2027. By 2030, RSA and ECC will be completely replaced by the PQC. So what is MLDSA? Module Lattice-based digital signature algorithm is a post-quantum cryptographic digital signature algorithm designed to provide secure integrity and authentication against the quantum attacks. So let us look into the key features of the MLDSA. It ensures a secure digital signature against the attacks from the quantum computers. And also it relies on the hardness of the lattice problem over the module lattices, making it robust against the quantum attacks. Like other digital signature algorithms like RSA and ECDSA, it has 3 primary operations: key generation, signature generation, and signature verification. In the key generation, it generates the key pair, private and the public key. And in the signature generation, it generates the signature using the private key. In the signature verification, it uses the public key to verify the signed data. It has 3 variants: MLDSA 44, MLDSA 65, and MLDSA 87. Let us look into that MLDSA parameter set. MLDSA has the 3 parameter sets based on the key sizes and the signature sizes. The security parameter also depends upon these parameter sets. The key sizes and the signature sizes used into the MLDSA is much larger than that existing classical RSA and ECDSA algorithms. With this, I have completed my part of the presentation, and I will be handing over to the Venkanna. He will be sharing his slides, and then he will be covering the remaining part of the presentation. Thank you.
Yeah. Hi, everyone. I'm Venkanna, Senior Manager at Marvel, leading the crypto team. Now that we have explored quantum computing, its impacts on classical cryptography, and the status of the post-quantum cryptography. Thanks to Dana, let's move to MLDSA and its modes and use cases. Coming to MLDSA, it provides two modes for signature generation and verification, as specified in the FIPS 203 NIST specification. So first one is the hash MLDSA, and second one is the pure MLDSA. In case of pure MLDSA, by default, pure MLDSA refers to one-shot variant. It takes a secret key, an optional context string, the message to be signed, and the mode as the inputs, and generates a signature as the output. MLDSA supports two modes of signature generation. First one is the random signature. This mode adds 32 bytes of random data into the signature generation process, resulting in a unique signature each time, even if the inputs are same. And other variant is deterministic signature. This mode generates the same signature for the same data inputs every time. And second variant is hash MLDSA. It is also similar to pure MLDSA, but it includes an additional input, that is pre-hash mode. Based on the pre-hash mode, it generates a digest of the message, prepends the pre-hash algorithm OID to the digest, and creates the pre-hashed data, that is PHM, as mentioned in this slide. The signature is then generated on the pre-hashed message. But both pure and hash MLDSA requires complete message for generating a signature, which can be a problematic for larger files due to the need to send entire data. To address this issue, NIST introduced the external mu option with minimal modifications to pure MLDSA. So as mentioned in this slide, this needs two operations: external mu based signature generation. Before invoking external mu sign, the application generates a digest of the message, and external mu MLDSA takes the digest as the input instead of message and generates the signature. And this performance comparison highlights classical signature algorithm versus MLDSA. The chart illustrates algorithms and their performance in operations per second. And the performance data is measured on x86 and system running at 2.40 gigahertz frequency. And all the implementations are done in software. And here, as shown in the slide, the MLDSA outperforms RSA and EC variants in speed. And also it offers enhanced security compared to RSA and EC. And here first, I'll give brief overview about TLS protocol. And TLS is a communication protocol between server and a client. The TLS protocol communication is divided into two categories: handshake and record layer. The handshake protocol basically addresses three major requirements, which is needed to have a reliable connection between server and client. First one is to specify which version of TLS will be used and decide which cipher suits or algorithms are compatible between them. And second step is key establishment using public key exchange algorithms and authenticate the identity of the server and server's public key using server's public key and the SSL certificate authority's digital signature. And third step is generation of symmetric session keys to use the handshake is complete. Coming to record layer, once symmetric keys are generated, the record layer uses these keys to encrypt the data for confidentiality and ensures its integrity. And here are the steps for TLS 1.3 protocol to establish secure connection between client and server. The client initiates the handshake by sending a client hello message, which includes supported cipher suits, TLS version, and a random values. And the server responds with a server hello message selecting the TLS version, cipher suits, and providing its own random values. And TLS 1.3 uses Diffie-Hellman-based key exchange mechanism. And here the server sends its digital certificate and key exchange parameters, including the public key of the chosen key exchange method. The client uses the server's public key to generate pre-master secret, which is encrypted and sent to the server. In session key generation process, both client and server uses the pre-master secret along with the client and server random values to generate the session keys. These keys are used for encryption and decryption of the data during the session. Once the TLS handshake is done, and client and server will have same symmetric keys, and they can communicate using those keys further. And here, this is the TLS 1.3 protocol connection establishment using PQ algorithms. Standard server authentication using PQ algorithms in TLS 1.3. The client initiates the handshake by sending a client hello message, to which server responds with a server hello message. In classical handshake, Diffie-Hellman is used, but here key encapsulation mechanism MLChem is used for key exchange. The client hello generates a MLChem key pair and sends its public key as part of the client hello message to server. Upon receiving the client's public key, the server performs chem encapsulation using this key and generates a shared secret and ciphertext. The server applies KDF to the shared secret to generate the all session keys. The ciphertext is included as part of the server hello message, and the remaining data is encrypted using the session keys. After receiving the server's data, client performs chem decapsulation using his private key to get the shared secret and applies KDF to the KDF and generates its session keys. The client decrypts the data received from the server and verifies the server's certificate and sends the key confirmation to the server. Through this exchange, both client and server calculate the shared secret and use it to encrypt all subsequent handshake messages. Symmetric keys are generated on both sides, are used for encryption and decryption of application data. So here we used PQ algorithms, so it ensures secure communication as both chem and MLDSA are resistant to quantum attacks from classical computers as well as quantum computers. Coming to code signing is a security measure used to ensure the integrity and authenticity of the software code. Main purpose of code signing is ensures the integrity and authenticity. And here digital certificate binds the identity of the person or entity to the public key and private key. And also it is used to sign firmware, software, scripts, and other executables. And also it ensures end users and customers code integrity and authenticity. And developers, organizations, use the private key so that other party can ensure the authenticity and integrity. And currently, EC and RSA based sign verify algorithms are used for code signing. However, both are vulnerable to quantum computers. Therefore, we need a new algorithm for code signing. And here, code signing with MLDSA. MLDSA is a post-quantum algorithm designed to provide secure digital signatures even against adversaries with quantum computing capabilities. Steps involved in code signing. First step is key generation. The signer generates a public and private key pair using MLDSA algorithm. And next step is signing the code. The signer uses the private key to generate the digital signature for the code. And this involves creating a hash of the code and then signing the hash with the private key. The signed code is distributed along with the digital signature. And coming to verification process, after the recipient uses the public key to verify the digital signature, This ensures that the code has not been tampered with and confirms the identity of the signer. The verification process involves checking the hash of the received code against the signed hash. If both are same, then whatever code is received is intact. And MLDSA support in DPDK. So DPDK currently supports RSA, Diffie-Hellman, and ECDH and ECDSA and EDDSA based asymmetric crypto operations. And even these PQC algorithms, whatever earlier slides, Dana explained, all comes under asymmetric crypto. So these can be added as part of asymmetric cryptography. And we can extend RT crypto AsymX form to incorporate MLDSA. And since PQC is a recent development and standards, and only have been recently released, it may take some time to implement these algorithms in hardware accelerators. So considering the quantum impact on the existing asymmetric cryptography, we can proceed with software implementation. Even latest OpenSSL 3.5 supports all these approved PQC algorithms. And data path for crypto devices which supports RTU security is enabled using standard RTE crypto dev APIs, that is RTE crypto NQburst and DQburst. As we discussed earlier slides, MLDSA needed more parameters than what was required for the other existing offloads, such as ECDSA and RSA. The MLDSA operation required all the fields mentioned in the slide. First one is the RTE asym crypto optype. The parameter specifies the type of the operation, either signature generation or verification. And second one is the prehash. In case of prehash mode, we need the digest algorithm type, but it is not required for other variants. As mentioned in the earlier slides, MLDSA has various modes, including pure MLDSA, external MLDSA, and a hash MLDSA. So the SIG optype parameter is used to manage the MLDSA mode. And next one is the message. Message is the input data or digest buffer to be signed or verified. And context is optional string. And the SIG is the output buffer for signature generation process and input to the signature verification process. And coming to current status, raw asymmetric PQC operations would be introduced, which would be used in TLS 1.3 protocol. The API changes are scheduled for 25xx release, and unities also will be introduced in the same version. And this feature is planned for OpenSSL crypto PMD only. This is our last slide, and we will now move to Q&A.
Okay, thank you guys. Any questions?
Thank you. A question. Did you do any tests on some equipment which could prove that the feasibility of this approach? Can you share results? I guess that's the speed of light.
Can you repeat it? Yeah, actually, are you asking for the PQC algorithm testing, or with the DPDK the testing are you looking for it?
So did you run any tests? I mean, you have shared your approach for support quantum algorithms, right? For TLS 1.3. So do you have any results, test results on test beds or something that you can share?
Yes, we can share it. We have tested based on the ACVP test vector, also that we have developed that one TLS 1.3 hybrid based one that we can share it.
Any other questions, guys? Looks like no. Okay, thank you.
Thank you so much.
Thank you.
straight away, right? Okay, yeah, and now we have Lukasz, right? He's going to talk about Regex offload within DPDK. Please welcome.
Okay, is the mic good? Okay, hello everyone. My name is Lukasz Ismich, and I came to talk to you a bit about my use of Regex device offload, especially in combination with acceleration of network applications. I'm from Slovakia, but I live in Czech Republic, so welcome. Okay, what was the main motivation behind this work is that I generally work and I'm part of Suricata intrusion detection open source team, and pattern matching there is really a heavy operation in these systems. So it can take even 50% of the CPU time. Generally, you have packets coming from the port directly to Suricata, and they spend the processing there. And this was in our analysis, but this is also supported by a different analysis that 50% is a good estimate of time spent for pattern matching. So when I learned the DPDK offers some Regex offload device, I was very enthusiastic, and initially I honestly thought it can be like a pipeline that packets would go from port through the Regex offload and into Suricata with some extra maybe metadata. What I was also enthusiastic about is that DPDK is of course the open source and vendor independent API, so it could be ported to any NIC. What I hope to deliver with this talk is my experience basically with the Regex API, what to maybe expect, and I haven't found many information from people using it, so hopefully it may be a help for future users of the Regex API. So right now, I would like to start a brief introduction to the Regex API in DPDK, then some comparison between the software and hardware offloads, and what are our current results with integrating the solution into Suricata. Okay, so the Regex API is actually in DPDK for 6 years. It's available on 2 series of cards, and that is Bluefield 2 and 3, and Marvell Octane TX2. It's a leukocyte accelerator, as I soon found out. So you cannot pipeline data from port to the Regex engine, but you need to receive them on the CPU and then send them to the Regex accelerator. What are the software alternatives to the Regex matching, and what are the commonly used libraries for pattern matching is Hyperscan from Intel. There is a branch from Hyperscan called VectorScan, which is more ported for ARM architectures, and libpcre2 is for the most generic Regex support that you can have in software. The Regex API is very similar to other APIs that you know from other DPDK sub-libraries or other modules. So you have some configuration part, NQ part, and other parts, and test regex is the DPDK provided example application that you can get your examples from. Generally, in the first step, in the configuration step, you configure the regex device, and then you have some set of patterns that you will want to load into the regex device. And then, when you are using the regex device, you generally receive, let's say, an MBUF from a port. Then you initialize the DPDK regex ops operation structure with the reference to the MBUF and some other configuration fields. And then you enqueue the operation to the regex device. What I would like to maybe highlight here, and what was a bit confusing for me at the start, is when you actually, let's say, transmit an MBUF to a port, or you are enqueuing object to the RTE ring, you should be like losing reference to the object, but this regex ops are just like helper objects, and in the enqueue operations they are actually just copied to some vendor specific object, and you are still reusing the regex ops. And then when the regex operation is received by the regex device, the device then reads the data that it needs to scan with the patterns it needs to inspect, and then it returns us the results, basically. It's a synchronous API, so you enqueue the operation, and then later on you dequeue when the device returns the results. What are the target applications that regex API was developed, the intent was developed in? It was exactly the intrusion detection system, intrusion prevention system, web application firewall, so basically some data-heavy operations, or maybe even host memory analyzers, so the application might not need to be directly network related. They might be just data mining or the memory analyzing applications as well. I haven't found any basically application that would publicly admit that use the regex API, so it's still, I think, looking for its very good use. But I found some exotic features, let's say, that could be helpful, and that is external buffer support, so you don't need to create special objects. You can reference the current MBUFs or part of them with the external buffers, or you can change them, and the regex device will still should inspect it as usual. I tried the external buffer support, but I didn't have luck with the Bluefield RXP. Okay, so previously I mentioned that there are the Bluefield 3, and the Marvel NICs. Bluefield 2 is quite common with Bluefield 3 as well. We tried to also get the Marvel, but we couldn't get it. We either had no reply or it wasn't in stock. But from I will present some let's say performance testing that we did, and from my information, it should the same regex engine should be actually in the Marvel NIC as well. And my assumption is that as in Mellanox or NVIDIA, both the regex engine company, the Marvel lost the opportunity to have the regex engine in there. To introduce the card that we were working with mainly, it's the NVIDIA Bluefield 2. It's the data processing unit, which I assume most of you know. But for us, it was really the regular expression engine in there that was of our interest. Here in this diagram, here we have, on the left, we have network port, and it generally goes to the host, let's say. And here is the Regex engine. It's in the Lucas Side Hardware Accelerator box. This Regex engine supports a subset of the PCRE standard, so you cannot put there any kind of regular expression there, but in general it supports, the support is pretty good. Other specifications of the Bluefield 2, it's 100G NIC. It has ARM cores, so you can use those as well. It's the A72 cores and 8 gigabytes of RAM. When we were kind of evaluating how to use the Regex engine, we were looking for the RXP benchmarks. So the RXP is the Regex engine in the Bluefield 2. And we found many works that evaluated the Bluefield card itself, but not the Regex engine. We found, let's say, these four main works, but all of them had very different results. So let's say the DPU bench had only 12 gigabytes of throughput, which seemed very low. Then some other works improved the throughput to 30 to 40 gigabits. And then NVIDIA provided benchmark, reported 51 gigabits. So we wanted to kind of test it ourselves. With this slide, I would like to highlight the NVIDIA's RXP bench tool for the benchmark purposes. Me personally, I spotted it a bit too late into the evaluation process, but it offers basically the connection to the RXP accelerator, to the evaluation with Hyperscan, with the software variant. It's within the Docker packages. And some tips on how to navigate within the NVIDIA docs is make sure you have the very latest version of the docs. It's not always when you click from the Google. And then suddenly, when I was on the right version of the docs, I could see that NVIDIA also published some benchmark results. And you can get the extended benchmark of the Regex engine from NVIDIA, but you need to ask and sign NDA, which we didn't want to because we wanted to also publish the results later on. So also NVIDIA, they basically had 3 data sets. It was the, let's say, Shakespeare, some port 80 and MEC CDC PCAP, and some the rows represent the rule or pattern sets that they were scanning the data sets with. And they also reported very varying throughput from only from 4 gigabits to 51 gigabits. So it depends. So we also wanted to try to test it. And in our work, we provided the open source Regex test application, which uses the DPDK Regex API and also uses the Hyperscan just so we can compare what are the results of individual pattern matching engines. And honestly, we're overloaded with the complexity. Regex engine is not easy task to benchmark. So in the end, we just went with the fairly simple benchmark of having packet gen as the packet generator, which was just generating same size packets. And as an input to the Regex engine, we were providing patterns and regexes from the intrusion detection system from Suricata. And one of the results was this throughput heat map. The X and Y axis are two different parameters which we were changing with packetgen, basically, and also the input rule set. So the X-axis is how many rules were loaded into the Regex engine, and Y-axis is how long the inspected packet buffers or the input packets were long. And from here we can see that if you have long enough packets and not too overloaded Regex engine, then you can really achieve the 51 gigabits of throughput. But if you go lower with the packet length, or if you go higher with the rule count, then the throughput is kind of going downhill pretty fast. In here, we also compare the Regex engine versus the Hyperscan, the software alternative on two platforms. On the left, we have the ARM cores that are directly on the Bluefield itself, and x86 cores on the host machine. The y-axis here is the maximum throughput, and x-axis is basically how we scale the Regex test application. The lines on the plots are the maximum throughput that the Regex engine achieved. Here it kind of copies the information, especially with the high number of patterns. If you overload the engine, then it's kind of stuck at the maximum throughput, let's say 5 to 10 gigabits. So it's definitely not recommended to use too much or too many patterns. Here I have some notes just to make sure I don't forget anything. What was very positive to see was that the Hyperscan is very well scaling with the number of cores. Let's say in x86 we can see the linear scaling with the number of cores. This scaling on the ARM and the Regex engine itself, it's not the scaling that the Regex engine would use more CPUs, but rather it's the low forwarding capacity of the ARM cores that they were just not keeping up with forwarding data to the Regex engine, and that's why the performance improves on the ARM and not on the x86. What we can see here basically, that if we compare the light orange line on x86 and light blue, that's the Hyperscan, we can see that with one core on x86 we can match the performance of around 8 x86 CPU cores. So you need 8 CPU cores for Hyperscan to match the same performance of the Regex engine, which can be pretty positive. But what is even more positive is when you look at the ARM and when you look at the light blue on ARM, it's rising pretty slowly, so you would need much more ARM cores to match the same performance as you have with the Regex engine. What is also interesting here is that Hyperscan, the latency, basically the time that you send just one operation to the Hyperscan and it returns back the result, was in this case around 3 microseconds, whereas with the Regex engine it was we had to wait for like 5 microseconds, but that is for a single synchronous operation. Where RXP can gain is because it supports the asynchronous operation. So you just tell the RXP to do its job, and then in the meantime you can do anything else. With Hyperscan you are busy doing the pattern matching, so that's why you can gain some performance with the RXP. Since you are loading the rules only in the beginning, you still want to have the rules in some smaller groups, because usually you don't want to inspect every buffer with the whole rule set. And we were wondering if we have many like little groups, the subsets, in our overall rule set, will it somehow affect the performance? And as we can see, with one group which contained all the patterns, it was 28,000 patterns, the throughput was degraded. But as soon as we divided into smaller subsets, the performance improved to the expected results around 50 gigabits per second. And even if we had 1,000 subsets, it's fine, and yeah, we don't need to worry. Now, how we implemented the regex into Suricata. So first, what is Suricata? Suricata is the open source threat detection engine. It's generally known as the intrusion detection system, so something that you mirror your traffic to. It's loaded with some security rules, inspects it, and has some outputs. Sometimes it can be in the intrusion prevention system, so lying directly in the data path or network path, but it can be also used as a library in your custom applications. Generally, people are interested in the signature alerts, so some outputs from the security rules, but it outputs other information as well. That is very useful when doing the cybersecurity operations. This is how, let's say, the rule looks like that's loaded to Suricata. It has some operation, and here we have, let's say, HTTP method get. Get is the string that you are looking for in the packet, or the rule is the string that you are looking for. What's the typical IDS processing pipeline? You receive a packet, HTTP packet. It's captured by DPDK, it's decoded, and then you have the first optimization that's usually in intrusion detection systems, that's dividing the overall security rules into smaller subsets of rules. So yeah, you don't want to inspect the UDP rules. You focus on the TCP and to server direction only rules. You can do some other kind of pre-filtering, but what we are mainly looking at is the pattern matching here in this talk. So in this orange box, the multi-pattern match is a way how you filter down only the, you will only inspect the rules that from which at least one pattern matched. Let's say you have multiple rules. One of the rules have the search as a pattern to find, and if you find it in the packet, as let's say here, it's good, and you can proceed with the overall evaluation. So the multi-pattern matching is the main CPU-intensive operation of the intrusion detection system, and that's what we were mainly looking at. It operates in multiple contexts. So the multi-pattern matching generally tries to be as specific as possible. So if the rule is concerned about HTTP, only is applied to HTTP packets. But packet payload is the most generic, like when it cannot match on anything else, it fallbacks on the packet payload, and it inspects just the packet itself. And that's what actually takes the most time. When we did some performance analysis of the IDS pipeline, we have some boxes on the left, which is the I/O operation, decoding, stream reassembly. But what is the most important here is the payload multi-pattern matching pre-filters and some other pre-filters here. And this red thing is what really interests us. But why? I will just explain it in a second. So when we wanted to offload the pattern matching operation, we had some constraints to consider. I didn't mention this, but for RXP, you need to have the inspected buffers in the huge page memory. Generally, Suricata uses the regular malloc free operation that dynamically allocates the memory during runtime. When I just converted it naively to RTE malloc, I found out that RTE malloc isn't very good at dynamic allocations that you do at the runtime. So that failed. You can also copy the desired memory to be inspected just before you send it to the RXP, to the huge page memory, but basically this copy operation was too heavy. That's why we focused mainly on the packet payloads only, because packets are residing in the huge page memory because we use DPDK. And we can send these the packet payloads directly to the RXP engine. Then the other constraint that we had to consider was the latency of the RXP engine, and we couldn't really wait for the RXP because it's longer. It has longer latency than the hyperscan. So that's why we opted for asynchronous offload, meaning we process packets, other packets, meanwhile we wait for the pattern matching results from the Regex engine. Then we also had to consider the rule set size. The rule sets in Suricata can have 50 to 100,000 rules. Those are pretty normal numbers, but those don't go directly, those are not directly searched. They are split into subgroups, and when we found out that pretty well-known detection rule set from emerging threats have around 2.4 thousand patterns, we knew we are in the safe numbers, because from the heat map we could see that we can go up to 8,000 patterns. And the packet size, we tried multiple variants, but at this time we have kind of like dynamic thresholding implemented. So if the RXP engine is not super busy, we send any packet to it, and if it's becoming more and more occupied with packets, we only send the more prospective packets, the larger packets, to the RXP. So PAMO is the let's say the proposed design, software design for Suricata. I think I basically explained this slide with the previous one. Yeah. So this is how we basically changed the operation in Suricata. In Suricata, the usual operation is run to completion. So one worker receives the packet and completely processes the packet from the start to the finish. In PAMO, as we were introducing the asynchronous operation, we pre-filter the packet, and if we see that, okay, we need to send it to the RxP engine, then we create the asynchronous job and send it to the RxP. If, let's say, the packet is only in a TCP acknowledgement, then we just finish the processing of the packet. Later on in the main processing loop, we are not only polling for packets from the port, but also from the Regex engine. And that's when we convert the results back, like we try to reinsert the packet into the usual processing pipeline, and we finish the processing. Okay, so here are some final results. The blue dots are the proposed system. The orange, what is it? Let's say rectangles are the baseline, Suricata. We tried it with the emerging threads open rule set again, and some academic trace that we captured and replayed on the system. And we can see that, let's say, if we look directly on 6 cores, the Suricata can achieve 20 gigabits, which is pretty good. But PAMO can achieve already almost 30 gigabits, so that's like 50% improvement. The red line suggests the difference between the two systems, and from the 6 cores we currently see the decline in the difference, and we need to evaluate why. But up to 6 cores we are very optimistic of the solution and how it can help to improve the performance. Then we also tested what's the effect of the number of rules in Suricata. Of course, if you have small rule sets in Suricata, it's not that effective because you have less rules, less patterns to inspect. So you need to increase you need to make it worth for the RxP to be enabled. So with the larger rule set, it becomes better. And some conclusions on the Regex engine as a performance benchmark, let's say, and the Suricata. Yes, you can reach 51 gigabits, but you need to be careful about the other constraints, such as the inspected buffer length. That's very important. Rule set size. What are the input data? And what are your patterns? So this can all influence your overall performance. The last 3 are kind of similar across all Regex engines, whether it's hardware or software algorithm. But the inspected buffer length, saying that little buffers can take more time or can degrade your performance more than the large buffers, can be quite counterintuitive. So you need 8 Hyperscan cores, and on ARM, it's very, very good use for the ARM applications, if you have any, to accelerate the operation on ARM especially. Some personal comments about how, for me, it was to work with the Regex API. The docs, mainly the NVIDIA Docker docs, can be pretty confusing, and there are not many other materials to gain information from. So you need to be pretty careful, and you need to do also a bit of your research as well on the site to understand how things work. And that's why I hope this presentation can help for others. I really wish the RxP could have a little bit better developer debug experience, because when I messed up with something, it only told me that there is some error, but not much more details. How we plan to continue with this work is to finish the exploration, chase the bug, and fix it. There are some other prospects, such as we only currently inspect the packet payloads, but we kind of leave the stream inspection on the table for the hyperscan still, and we can still contribute this exploration to Suricata code as well. From industry perspective, I need to tell that the NVIDIA decided to drop support for the RXP from Doka 2.5, and in Bluefield 4 we will probably have some AI accelerator instead of the Regex engine. With Marvell not offering, or we couldn't get the Octeon cards, there are no vendors currently for the Regex accelerator, so I'm hopeful that it will motivate some people to reintroduce it. And if there would be possibility to have the pipeline pattern matching module on the commodity cards, that would be amazing, I think, not only for the IDS but for other applications as well. Okay. So that's it from my presentation. If there are any questions, please ask.
Yes, here. Thank you. Did you test in Regex? There's usually needs more than one buffer. Did you? All the Regex information matched a single buffer, a single message, or you need also to sliding window with it, and you tested it with sliding windows and such techniques, or combining basically number of MBuffs together, the chaining or something like this?
No, generally we didn't test this because the Suricata itself was not ready to chain buffers together. So that, like, we generally receive the packet, and then Suricata, as it processes packet one by one, we evaluate the packet itself on the spot, whether we need to send it to the Regex engine or not.
Hi, yeah, thanks for the talk. I have a question regarding the performance tests you did. So you mentioned, so the performance tests on CPU were with Hyperscan, right? And you also mentioned in the beginning of the talk that the Hyperscan has a different, like, fork, maybe a vector scan, which is specific for ARM. So I'm guessing, so what I'm wondering is, did you use vector scan for the ARM testing?
Yeah.
Yes.
Yeah. It's generally, we went with the recommended approach and we used the vector scan.
Okay, thank you.
Thanks for the talk. So the setting of your problem is very similar to the one we had with ACLs and asynchronous. So I have a question regarding the Regex engine. Do you have any guarantees on the orders of the requests that you receive? Not the requests, the results you're receiving back from the engine. Do you
like handling basically the reordering?
Yeah. Or do you need to do it in the app?
Yeah. Not necessarily, since we mainly focused on the intrusion detection system, which doesn't send any packets any further. We didn't need to deal with the order of packets when transmitting elsewhere. With regards to the detection, from our, let's say, knowledge, before we send it to the Regex engine, we let's say, note down all the needed information for let's say, detection or reassembly of other packets. So we only receive results back with the actual matches. So I don't think we had to really reorder packets as you did in your talk.
Got it. Thank you.
So did you also try Intel Hyperscan with the QuickAssist technology? So it's kind of a module to, to speed up probably encryption, decryption, but does it really help in this case for Hyperscan and Regex?
Sorry, I didn't get the module.
So it's a QuickAssist technology.
Okay, no, I don't think we did that. Okay. We just, it was either installed or compiled by hand, the Hyperscan, and unless it was doing some automatic detection, then we didn't use it.
I think for QuickAssist, sorry for interrupting, you do need a special hardware. Not all Intel chips do support it, as I remember.
Yeah. Okay.
Yeah.
Is it a CPU chip, you mean?
It's system on chip.
Okay.
Well, as I remember, it was a while when I used it, but it supports both modes. It could be just a pluggable PCIe card, or it could be system on chip. It depends on CPU model, does it support it or not.
Okay,
yeah.
Okay. And maybe one more remark for others. It's I think good to mention that the Hyperscan is being closed source again, unfortunately.
Wow, unfortunately. Any other questions, guys?
Hi. What's the machine you used for the testing? Because it just says ARM and 86.
The x86, the Intel Xeon Silver.
And the ARM one?
Yeah, this one.
And the ARM one? What was
the ARM?
What machine was it?
The ARM machine was, it's the ARM CPU directly on the Bluefield card itself. Sorry. So Bluefield 2 has the ARM CPU cores. It runs basically a separate operating system on the DPU itself. So that's where the vector scan and Regex engine was running.
Which version did you use of VectorScan?
I think we tried the latest, but I don't really have the information.
Just wanted to point out it's not ARM specific VectorScan. It's all architectures, including Intel and everything else.
Okay, I think that's it. Thank you very much, Lucas. Very interesting one. Okay, and now we have Vitaly Ivanov, if I'm not mistaken. He is from Niagara Networking, and he's going to talk about next generation ASICs for next generation network and all this within DPDK.
Yeah, I'm good.
He's welcome.
Just to support my power, just in case. Yeah. So, hello everyone, good morning. My name is Vitaly Ivanov. I'm part of Niagara Networks, and today I'm gonna talk on the subject beyond standard ASICs, and creating and using custom hardware with DPDK for next-gen networking. So it's a fancy name, but at the end of the day, what I'm gonna do is just to describe our experience in creating such an environment that is basically giving us ability to touch every packet and do customizations on traffic processing. And that's basically the environment that suits our needs. So it's not going to be kind of too detailed and advanced topic like previous speakers did, but at the end we do a lot of this advanced processing. For example, like Lukasz just described it, we do also Regex on traffic based on this environment. So agenda, it's a brief introduction about ourselves, problem statement, solutions that kind of we created in terms of hardware and software. Just probably a little bit of our environment, how we organize the process and develop and test all this stuff together. Niagara Networks, it's a global privately held company, with the headquarters in the Bay Area in the Silicon Valley, and R&D offices in Europe, Ukraine, and in India, and also global sales and business development coverage for the world. Basically, the company started in 2016 as a spin-off from another our mother company called Interface Masters that basically operate as an OEM and ODM vendor and create basically design, manufacture different networking equipment like switch appliances, Ethernet switches, NIC cards, and many other things. And Niagara Networks adds on top of that hardware, software stuff that that we sell basically. And again, so this talk is about to share some, knowledge and experience from the people that are trying to work with DPDK on our side. So we do not contribute a lot back to BTK. We report some bugs and some small patches, but at the end we are just trying to use it for our needs. So the main product lines that we have for Niagara, it's packet brokers, it's bypass switches, tabs. We also operate in cloud. It's a virtual packet broker, tabs, and at the end we have a software that can orchestrate all of that. So problem statement, we as vendors that create different hardware from different vendor silicons, we are always limited in functionality, so we want to do more with packets and basically be able to touch every packet like what you can do in software. And there were some attempts from different companies like Barefoot or now it's Intel Tofino. Broadcom also proposed like NPL language for their ASICs, but at the end it's never get to the, so we know that Barefoot is kind of end of life right now. Intel is not selling the stuff anymore. NPL is also not there, to do the kind of stuff that we want to do. So our main, stuff that we want to achieve is be able to touch, basically every packet and do what we want to do with that. Kind of unite hardware speed and software flexibility. For that, simplify operations and do the full abstraction from the user. And one more kind of important point is to create a platform that will be able to run not only our applications, but applications from other people with the smallest possible touches to that software. So for that, we created a platform. We call it all-in-one Swiss Army knife visibility solution, but it just basically it goes in two modifications. It's a 2U system or 1U system. I'll just stop on 2U system for simplicity. So it has 8 bays that you can place different modules inside. So it's field replaceable modules. We are targeting 19-inch data center rack. The system is based on Trident 2 Plus from Broadcom. And so inside of this box you can plug different functionality modules like network taps, bypass, packet brokers, and the module that basically I'm going to start today that we call intelligent network traffic processing. So just for you how it looks, just to get better understanding for the system. So it's a front, rear, back view and 3D view of the system. And I was afraid that the slide is going to be too small for all of you guys to see, but just a brief summary. So that's a variety of modules that we can support on the system, and again they have tap, bypass, and PB functionality. And these modules have like throughput from 100 megabits to 1G copper, 1G, 10G SFPs, 40G, and 100G modules. And the last module that is kind of in this red square, so that's the module that I want to talk on today. And the main difference for this module from all other modules is basically it doesn't have any front panel ports. So very basic how a regular module look like here. So it can be 1 or 2 bay wide. So basically you can insert 8 or 4 modules if they are in maximum capacity. Each slot has some limitations, power SRDS. The central point for this is CPLD FPGA. And this through extended serial bus and FPGA, we have access to ASIC-RC and SFPs. We can do diagnostic of SFPs, access temperature sensors, and many other things. So we also sometimes we have this PHYs that do the different, let's say, port configuration. There was also a plan to support a hot swap. So imagine that the system is running 8 modules and 4 of them are processing traffic. And so during the operation, you decide that you want to remove one of the module and just plug another one instead of that. So that's kind of reachable and available in first releases. So we did it through Broadcom API mentioned here, but at the end we completely just dropped this functionality. It's just too complicated to maintain. And for more complicated modules, it just requires more effort. But at the end, a regular model here, it's more like just to see the full picture, but that's not our point of interest for this talk. So what I really basically want to describe today is modules that we call Packetron. So it's a trademark, and it consists of 2 parts. So it's a COM Express module, Type 7 standard, and also customly designed carrier board. So imagine that you need to insert it into our system, use a standard connection, I/O connector for this module, and so on. So this carrier board is what we do. And also we basically extend this carrier board with the functionalities that we want to have. So as part of this carrier board, again, we have a central point, CPLD FPGA. We have a I210 controller for management port. We also have 2 Ethernet controllers from Intel XL710 connected on the one side basically to I/O connection, I/O connector, and on the other side they are available to our COM Express module. So this basically this configuration can have SSD up to 2 terabytes and RAM of up to 128 megabyte. So you can imagine that we are going to utilize this Ethernet controllers as port for our board, and basically we configure them to run in a mode of 1 Ethernet controller. It's 4 ports by 10G. So variety of different ComExpress modules that we can support here. So we work with, it's like two basically main vendors. It's a Congatec and AD-Link, but just not a super big deal. So what I'm basically targeting today, it's Xeon D1577 16 cores with a base frequency of 1.3 gigahertz. And so the module is inserted to the box, and you know, the idea is that these Ethernet controllers are connected directly to ASIC switching silicon. So what we do, we use a special connection type that is called backplane. And for this Ethernet controllers, we put a special firmware from Intel that defines not only speed, but also this backplane connection, and what is also important, port order. So here we use 6.01 firmware, and later on you can see that on S tool if you just want to see the firmware. So what it does, again, it connects these Ethernet controllers to ASIC. So you can imagine that you have a plain configuration from ASIC to Ethernet controllers. So on the other side, on ASIC, so when you do this connection, like it's probably, you know, people that work with ASIC, it's a common issue, but we have this TX, RX port swapping. But because 4 ports on Broadcom sites, they are part of one TSC core. So this can be really easily addressed on Broadcom side by just defining correct variables that address that. So once we do that, the port 1 on ASIC side will talk to Ethernet 1 on TX-RX and vice versa, so back. So with that, once we do that, we have a plain configuration between our Ethernet controllers and ASIC. And so, you know, it's completely not it. You have to do a lot of other things to operate and, you know, start using this environment for your DPDK application. So what we have here, from all the 8 basically base that we have on the system, you can add plugin Packetron into all of them. So you can use only 4 base. They are shown here as in green, just because, first of all, you know, this module doesn't have ports, right? You need to take traffic from somewhere and deliver it back to the world. So we decided to divide this platform at like half and give a user ability to deliver and take traffic back from the system. So once you imagine that you insert 4 of these Packetron modules to the system, and it means that you have basically 5 PC or 5 CPUs talking to each other, right? So you have a host CPU, main CPU that controls the whole board. It's shown here as it's a bigger box on the screen below. And it talks to 4 Packetrons, so it's the connection that is available is management port, and our software is talking, you know, JSON RPC custom created. But the only, you know, stuff that is available to outside world here is this host CPUs from management interface Ethernet 0. So that's why we support our web GUI interface, Cisco style CLI, SNMP, REST, and all other stuff. So if it goes to, you know, next modules, you simply cannot reach them from the outside world. So that's the stuff that's internal and completely hidden from the other people. So with that, you know, imagine that you place the configuration, you're booting the system, and it's kind of, we are getting to the point that you need to operate and handle software on not only on the management main CPU, but on all these modules that you can place on the front panel. So for that, we basically we use Pixie, because it's an Intel CPU on Packetron modules. We use Pixie. So the system is configured in a special way that once it detects that there is nothing on the SSD, we just go and try to talk through the management interface. And for that, you need to handle this network. So we maintain an internal DHCP, so it's called static DHCP Python-based tool. So it's much more simplified than a regular DHCP server, but it basically does all the stuff that we need. So it responds to DHCP. It provides back to someone who is asking the software to install load into memory and do all the magic. So as part of this infrastructure, we also have to support TFTP, NFS, IP tables, basically to hide packettrons from external world at the same time, to configure correctly routing so that they can sometimes, let's say, talk to through the management board to the external world. So custom operating system, this is what we place to the packetrons. It's Debians, but at the end with a custom kernel. For speed optimization, we try to create images as small as possible to speed up things. No BMC model here, so all of that stuff is managed through CPLD. For example, here, if you place a correct, value to our SysFS3, so basically all the low-level stuff we provide through SysFS. So all the registers of CPLD you can access on SysFS3. You basically switch through this RS-232 UART register, and you can connect to console port of each model. So you can see the whole boot process, you can get into BIOS and do all the stuff that you need to do. So with that, we have, on the previous slide, it shows that how we connected data ports. Now we have the whole infrastructure, let's say, for the booting up the modules, placing operating systems, and let's say everything is prepared to run your DPDK applications, right? But before that, the slide that is very important for us, so it's optimizations for DPDK, and so BIOS is a very important thing to tune for running DPDK up, and probably all of you know that. But if you go to your website and check performance reports, what people do to get maximum performance for testing stuff is just disable CPU C and P state, like for energy efficiency, and just run on the maximum. It's very often it's just not enough. So every vendor provides different BIOS. All of the settings are just hidden, and you have to play a lot with this, this BIOS just to tune what you need. So I hope that this slide can help to some people, but at the end, yeah, we set CPU performance and power mode to performance, disable C state and P state. We also disable basically turbo boost, even though on the performance report some people use it, but just because this module is part of the whole system, so we assume that you have to run traffic for hours, days, weeks, or even months, right? Once you configure all of this stuff, you just do not touch it, and device is just processing traffic. So turbo boost is helping with, let's say, minutes of speed up in performance, but based on our testing with a lot of traffic, once you pass this, limit and CPU resets, so you get into the mode that gives you even more problematic performance that you have on the base frequency. So you just get into this state, and only reboot basically helps. So thermal monitoring disabled, hyper-threading disabled as well. We also here, so we have this booting process, configuration of PXE, and stuff like that. Also important thing to mention, on the other side. So once you pass the BIOS and boot in your operating system, you also have to play with settings. So a few important, it's definitely CPU affinity. So as I said, we are talking right now about Intel Xeon D1577 that has 16 cores. So what we do, we allocate to operating system and for our management communication only one core, and all the other cores we just allocate to DPDK apps. Huge page size and other things that are also pretty important. So with that, yeah, we are going to software. I'm not going to describe a lot here. Again, the main kind of requirement for us is to run this in a steady state, right? Super reliable and stable for quite a long time. But at the same time, try to get as much performance as possible from the system. So some details for our application that is customly created for this kind of environments. So it's run to completion model, optimized core TX, RIX, queues allocation, symmetric RSS. We use quite a bunch of libraries from DPDK. And basically two mods that we support at the end. So it's a bare metal, where the application and the operating system that we install in, it's right on top of the hardware. We can also support VM mods, that's VMware ESXi, or open source one XCPNG. So this is done just to to have this the platforms that I mentioned initially to support third-party application. So imagine that if you have a hypervisor like ESXi, you can allocate different parts. You can create few VMs on that system, allocate some resources to our application, less ports, less CPU, and can even run some VMs like, I don't know, Suricata, for example. And all of that is integrated into GUI. Big part of that is hidden from the user. So the kind of what we were able to achieve as a result of that, and our advanced software functions that we were able to do here. So it's a nice list. So packet and flow slicing. So imagine that we work in the field of network visibility, right? So via NPB, we provide right traffic to the right tool. So let's say that we need to send part of the traffic that we receive on the system to next generation firewall for some monitoring or just some analysis, and it may charge you for the amount of traffic that it can get. So packet slicing, you can cut packets in size and just decrease the amount of traffic. Flow slicing, it's termination of flows. Traffic duplications, like when you have in your network duplicate packets, you can remove them. So NetFlow and IPFix. Somehow on Broadcom Trident 2 Plus, if you do not have this functionality of the box, you have like SFlow support. But people want to have more, and NetFlow and IPFix is what they're looking for. Data masking in Regex. So Lucas just talked on Regex. So if you want to have some sensitive, let's say, information, send it to some other tools for monitoring, you can just, before that, you can just try to mask, information that is kind of, some other people should not see, and that's what's used. L7 application filtering, so DPI, deep packet inspection on different levels. And so we can filter, for example, video traffic like Netflix or whatever. TLS decryption and man-in-the-middle mode, decryption, GTP correlation, it's mobile visibility when you want to correlate gTPC and GPU traffic, and mobile and carrier vendors, they would like to see this functionality, and again, it's it's pretty helping them. So tunnel termination and header stripping, it's a bunch of tunnels that can deliver traffic to us and from us, and big amount of them are also not supported on ASIC itself. Pickup dumps, so it's we are using pickup energy for that, library from DPDK, some protocol reporting and other things. And I wanted to especially stop here on this small GUI, it's a part, like a screenshot from our application. So here, imagine that you want to take traffic from input port. It's like a drop-down screen where on top of that you can have some ports and filters that you created. So let's say we want to deliver traffic from port 1, I believe, to port 2, whatever, but between these two ports, and in between do some kind of processing. So if you put a first box that states parcel filter, that's basically the functionality that exists on ASIC, and when we configure the ASIC through the main SDK, Broadcom SDK. But then if you just drag and drop a box like a flow slicing profile, so that's when the magic is happening, and this traffic on the ASIC side is just forwarded from port 1. You do first set of processing, then you forward it internally to our Ethernet controllers, do the processing there, and send it back to ASIC and forward to the output port. If you just remove this box, again, flow slicing profile, it's just, again, working purely on the ASIC side. So as a summary, of what we were able to achieve, it's kind of sandbox where we can play constantly and add new functionality and stuff that is not supported on ASIC. So we do not have dependencies to ASIC vendors SDK. So if you have right now a box on Broadcom, you can migrate this architecture to other ASIC vendors, and it will just work. Simple and hidden from user, bare metal VM mods, and third-party vendors support. So for sure, there are limitations. You probably, people that work with DPDK, you see them. So it's not super powerful CPU, and throughput and scaling. So imagine that one packetron can process 80G traffic on the input, and you want to scale that to like 200 or to 150 G of traffic, right? So you just insert another box in the system, and it's working pretty well if you work with features that is stateless. So it doesn't have a state like B-slicing. So it's just cut a packet based on the configuration. It may update checksums just for this packet to be valid, but at the end it's a pretty stupid feature, right? But if you want to support more advanced stuff like GTP correlation, so you process all the GTPC traffic, you create a database, you store this information, and on each GPU packet that you receive, you need to consult basically with your database for GTPC traffic. So in this case, scaling, it's not easy, and you have to kind of create a communication between packetron modules themselves, and that's kind of, it's possible, but we are not doing it right now. So our, CI/CD is just a slide that I decided to add here just to show the beauty of DPDK, and it's a complex device, it's a big device, and we have two teams, right? It's an ASIC team and DPDK team that work together. So when ASIC team is ready to start integrating new feature into this big box, let's say, so we already need to have all the functionality to be ready and available, and for that we use kind of environment, usual environment for DPDK with NICs. So we have also NIC created by interface masters, XL 710 Ethernet controller. You can just place it whatever, how many you want them, and just do the development. And as part of that, we have like a custom framework developed for testing. It's based on PyTest, SCAPI and pickup. So basically, it's a feature testing. So we fully test, we fully send traffic, we receive it, we activate all the hardware offloads on the NIC, and fully simulate what you can have on the final box. And it's not only for traffic, so it's fully testing all the parts of the application, starting from management protocol to all other stuff. So we use as scheduler Billbot, not Jenkins. Somehow we stick to that. It's just Python-based, not Java. It's less resource-eating stuff. We have summaries on a daily basis, just because, not on per commit, just because it's taking time. So this suite that I show here, it was running like 4.5 hours, a lot of different test suites. So we have these emails in the morning, basically, so tests run through the night. You have a summary that nothing is broken, and detailed reports that you can check later on in Allure. And yeah, the final slide that I have here is on Niagara Network. So we have a bunch of stuff available off the shelf, and we can work on custom designed solutions. So all the stuff is designed, engineered, and manufactured in the USA. Yeah, right now it's probably a tough time to discuss this kind of things. And kind of this slide describes our infrastructure. It's a technology kind of alliance with different vendors that we have. And with that, I'm going to say thank you. Thank you for listening.
Okay, any questions, guys? No? Okay, then thank you. I think we have a lunch break now, right, Nathan? Yeah. Until 13:35? Yeah, okay. Enjoy, guys.
Recording stopped. Recording in progress.
What? Oh, it's working. Yeah. So our next speaker was Mohamed Sefula, talking about database, but unfortunately he doesn't show up. I'm sorry about that. So for database discussion, maybe next year. So it means we have a bit more time, just sorry for interrupting your discussion. We will start at 13:50 for the next talk, and it will be a remote speaker. So in 10 minutes. By the way, hello everybody, and welcome.
Hi, my name is Tobias Roeder. I work for Rohde & Schwarz, and today's topic is Forget About It, benchmarking of flow timeout algorithms for RTE hash tables. The user story is quite simple. As a DPDK developer, I want to benchmark different flow timeout algorithms so that I can integrate various use cases such as IPFix or NetFlow probes, load balancers, firewalls, or in the telco space of 4G packet gateway or 5G user plane functions. Essentially, any integration that requires a stateful connection tracking could be applicable. The scope of this lightning talk is to extend the existing RTE hash cuckoo hash table with timeout algorithms. We are using and checking out also LRU, least recently used tables, as a performance reference. However, those do not really apply for most use cases since their timeout behavior is unpredictable. The 4 candidates we will discuss are timer wheels, skipless, LRUs, and periodic scanning. Timer wheels were already introduced in 1987 in the SOSP paper. Skip lists and LRUs are by default part of DPDK, and periodic scanning will be implemented in FlowGet. Let's start with the timer wheel. It's a circular array essentially where each slot represents a time interval. Timers will be assigned to each slot based on their expiration time. One improvement here or next generation is the hierarchical timer wheel that implements multiple wheels for certain time granularities. So this could be seconds, minutes, and then hours. On the other hand, skip lists are a more probabilistic data structure using sorted linked lists. So essentially on the base level, we have a fully sorted linked list with all the nodes. And as higher we go, we essentially have a skip list or fast lane that is able to jump over certain nodes for faster search operations. The LRU, least recently used table, is a fixed size table with different integration options. It always comes with some sort of LRU eviction list. In case of DPDK, they implement a bucket-based approach that resolves the most recent versus least recent entries for up to 4 keys per bucket. Periodic scanning is a quite lazy algorithm. It simply scans through the entire hash table in a predefined interval. We improved that operation. Instead of going step by step through the table, we defined a bucket or slice of 1,000 entries. So essentially, if we want to iterate through the entire hash table for 1 million entries, it only takes us 1,000 operations to scan for the expired entries, shown here in red. In order to qualify the performance difference on paper, we can apply the big O notation. So we have constant time complexity for insert, delete, and expiration for the timer wheel. We also have constant complexity for the LRU insert and delete. Same for periodic scanning. Periodic scanning has a linear complexity for the expiration process. Skip lists come with a logarithmic complexity for insert, delete, and expiration. So let's now measure these 4 different candidates. Before that, let's define the architecture of FlowGet. The architecture here is a thread local design. We are using the FlowGet library in the base integration of layer 2 forward. And there we conducted single core testing for non-drop rate RFC 2544. For multi-threading in future, you can use the sharding paradigm via, for example, symmetric triplets RSS. Let's zoom in. Before we discuss the hardware, a big shout out to the AMD Telco Lab. Kiseng Song was kind enough to provide this test setup. Thanks again. On the left side, we have an AMD EPYC-powered traffic generator running T-Rex version 306. On the right-hand side, we have the device under test running DPDK 2311. Both of them were running Ubuntu Server 2204. Let's take a look at the architecture of the APIs. The three most important APIs are flow table create to spin up the instance, so it takes the flow table type, either skip list, wheel, smart scanning, or the LRU, and a configuration for that table. Flow table process is the most important API. It takes the instance of the flow table and a burst or array of M buffers. It also requires an externally sourced timestamp. Flow table destroy gracefully shuts down the instance. Before we measure, we have to define T-Rex test profiles. So the first profile is the DNS profile. It's a simple query and response. That means we only have 2 packets per flow. That yields a very high insert rate of 50% and likewise 50% lookup rate. However, for a more realistic telco-centric profile, we define the telco top 50. This includes the 50 most used applications plus their corresponding DNS flows. That results into 1800 packets per flow in average, and a very low insert rate and a high lookup rate of 99%. Before we discuss the results, let's share here the configuration. We always measured with 10 million entries per table. We were using hash CRC, and the flow key was 64 bytes. The timeout selection was for the top 50, 30 seconds, and for DNS, much shorter, 5 seconds. Before we zoom into the results, let's run one example use case. So here we are on the actual server. Let's, for example, verify the CPU. And also let's take a look at the binary. So here we see we have standard RTE DPDK dependencies and also one dependency to libflowget compiled on the target. Before I can measure, I will need to start the instance. I do this by providing the standard layer 2 forward config options, plus here an actual table type, which is the scanning approach, lazy scanning, 10 million entries, flow expiration of 5, and a burst size of 64. After waiting for the instance to come up, we can discuss quickly on the left-hand side the T-Rex options. So here we are using the telco profile at a load factor of 50. And as the first flows and traffic comes in, we can confirm that we are not dropping any packets. And since we've selected a short timeout, we should see very soon first entries deleted by timeout. So this will increase throughout time, and here we are actually using the scanning approach. Awesome. Let's go back to the actual results. For that, I will zoom in. We are using Plotly to visualize all the results. So on the top half, we're going to have the top 50 telco profile for 30-second timeouts. Left side is gigabits per second, right side million packets per second. Here, LRU will always be the winner, so let's discuss the second best, which is the scanning. Scanning at 64 burst size yielded 79.5 gigabits per second. Respective, that translates to 9.9 million packets per second. If we take a look at DNS, LRU is by far the best performer. However, here we notice that the timer wheel at also a burst size of 64 is the winner, and it has 2 gigabits per second, respective almost 3 million packets per second. So let's sum up. The call to action, or do not forget about it. Periodic scanning yields the best results for the telco framework. However, we have some concerns regarding jitter and latency due to the burst eviction. Timer wheel has the best overall performance and precision. So the question is, why not add a timer wheel to the DPDK library? LRU is the best performer, no question. However, it's not really applicable for most use cases. It's more a caching approach. Future topics for benchmarking could be hybrid LRUs with eviction signaling, applying certain Bloom filters like Cuckoo++ research, or hardware-assisted aging, for example, NVIDIA Dockerflow. Thank you so much for tuning in.
Hand off to Konstantin to someone else. I was going to hand it off to somebody else this afternoon. Is that okay? I'm going to pull up the schedule for this. Does anybody have any questions for Tobias? Lucas?
Thank you for your talk. I had a question. You mentioned the telco top 50 profile as a T-Rex profile. Is it a profile that you created yourself, or is it publicly available? And was this profile run in the advanced stateful mode in T-Rex or in other mode? Or maybe I can just follow up with him on Slack.
Yeah, I'm looking to see if he's in here. We can actually put the question on the YouTube if you want.
Okay.
You want to just type that? We'll have him. Is Tobias still there? Is he still? No, he dropped off. Okay. Oh. He says, yes, it's a stateful profile. We recorded each data plane flow with TCP dump and real UEs. We can share the profile for testing.
One more question. So you showed the table, and the timer wheel has some advantages. And in the conclusion, you kind of asked why not to add the timer wheel to DPDK. Is it still an open question, or is it something to resolve there? And you also showed in the performance results that the timer wheel had worse results than the other, let's say, LRU algorithms. Is it because of some architectural reasons, or why is that?
So I guess we're waiting for his answer. So what we can do is, in the meantime, while we're waiting for him to answer, I can go ahead and introduce, I guess, the next talk, which is Adam Krapolsky and Eliska, mispronounce this, Chervenkova from CESNET. He just answered here your question. He said, LRU is not really suitable for deterministic timeouts, hence timer wheel is the best compromise. Hmm?
Okay, can we start or?
Go ahead, feel free.
Okay. Hello everyone, my name is Adam. I'm a junior developer at CESNET and a student at Masaryk University here in Czech Republic in Brno. Sadly, Eliška couldn't join me today, so I will try to present her part of the presentation or summarize it. So I'll be talking about how we try to accelerate Suricata with the RTE flow rules and to give some background about RTE flow rules and how we did it. So on my agenda, I will be talking about how to, or what is Suricata in general. Lukas gave us a nice overview, so I will try to just summarize it. Then I will be talking about RTE flow rules, so we are all on the same page. I will be talking about how we needed to rework the RSS that was already in Suricata to support our acceleration. And then I will be talking about the specific accelerations we did in Suricata. Those are the static drop filter and the dynamic bypass. So about Suricata, it's an open source network detection engine developed under OISF. It can act as an intrusion detection system or intrusion prevention system. It's based on, it matches traffic based on signatures. As you can see, here is an example of signature like this. It consists of 3 parts. Here is the action part that basically tells the Suricata what to do. Here is the header. It consists of the protocol, of the IP addresses and the port, and also it states the direction of the flow. And then there's the rule options or the signature options part, which can contain a variety of keywords which we utilize in the bypass. One specific one, I will get to it later. Also, Suricata supports multiple packet acquisition modes. For example, AF packet, PF ring, or the most important for us, DPDK. So Suricata, as an intrusion detection system, lies behind the firewall in the network. It can issue signature-based alerts. It can export flow information. Also, it can extract files, certificates, keys, or record PCAPs for later analysis. What was our motivation behind accelerating Suricata? As Suricata can work in a high-speed environments, there can be peak moments in the traffic where not all traffic is analyzed, and during these peak times there can be flows that are unwanted and we know they are safe, so we can not analyze them basically and offload this dropping or this filtering into the NIC, into the network interface card. As I mentioned, we implemented it with the drop filter, the static filter, and the dynamic bypass. And our goal was to stay as generic as possible to the hardware we support. So those are NICs with MLX5, ICE, I40E, and iXGB PMDs. And we are also supporting this feature across different DPDK versions, supporting from version 19. Okay, so how we did the acceleration. I will give some background on the RTE flow rules at the start. RTE flow rules are generic rules offloaded to NIC with the help of the DPDK API. So the DPDK application calls on some DPDK function, RTE flow create. The function creates the rule inside of the NIC with some parameters that I will get to in a minute. And then the rule acts there independently of the application. So as a structure of the RT flow rule, it contains attributes which basically define how the rule works or how the rule acts. There can be, for example, ingress egress, meaning if it's supposed to match incoming or outgoing traffic. Priority group, those are helpful when trying to organize or making some hierarchy of different rules. Yep. There is the matching pattern part, which specifies what flows to match. You can specify different protocols, also some of their specification. For example, you can see we can specify some IP address or yes, and actions. There is the actions part. We can utilize different actions. For example, RSS, drop, count. There's many more. Those are the main ones we are utilizing. So about how we needed to rework the RSS. Before it was initialized by the structure mentioned here. But we lacked the ability with this approach to chain the rules together or make some hierarchy with RSS. So we wanted to avoid the situation that, for example, the packets would be dropped or wouldn't be dropped because first they were redistributed with RSS. So we need to rework the RSS into the RTE flow API. Yes, we ran into some issues. It was a quite complicated task because not all the time I could find specific examples how other application utilize it on the specific NICs. So yeah, and when we were implementing it for 4 NICs, it took some time to figure out all the specifics of it. And also we were implementing it throughout different versions of DPDK, so that was also a drawback on the time. Some of the functions we ran into, for example, hash functions hash function support of the RSS were different across versions. We needed to catch this. For example, MLX5 support or needs just one generic rule for all the traffic that comes into the NIC and can redistribute the traffic just thanks to this one rule. But for example, for the ICE PMD, there is one rule for the IPv4 traffic, one rule for the IPv6 traffic, and the L4 protocol doesn't matter. But for the I4TE, there is separate rule for each IPv4 combination with each L4 protocol and different rule for each IPv6 combination with all the L4 protocols we support. So yeah, that was about the RSS stuff we did. And now to the main part, the acceleration or the offload we did with the drop filter. So the drop filter is a BPF-like filter built on RT flow rules. The rules are loaded to the NIC before the start of Suricata. They are predefined in the configuration file of Suricata. I will show you an example in a minute. And the goal was to reduce the load on Suricata so it doesn't have to analyze all the unwanted flows. As you can see, the example, it's quite simple. The NIC has some rule with a specific IP address. In this example, there are incoming flows. The flows are not matched, so Suricata analyzes them. The flow is matched. Suricata doesn't analyze it. And what flows can we leave out of the inspection or the analysis? Usually, those are verified or safe flows. Or flows with, there can be flows with forbidden inspection, that by some authority it was forbidden to inspect them. And some of the flows, like we know there are verified or safe flows, are some streaming services or when we have a private server with data backups, yeah, we don't need to inspect that, so we can leave Suricata to do more important work. How does the Suricata operator define the rules? We were inspired by the test PMD syntax, the DPDK test PMD application, sure know. But we just took out the pattern part. There is an example here. Just this is the full string that would be in the configuration file for matching one specific source and destination or flow with these parameters. As we do not support full BPF capabilities, we were not thinking about or we didn't approve of the BPF syntax, but there are still ideas and we are still a little bit brainstorming about how we could improve the syntax. So if you have any ideas, feel free to let me know after, and I will be grateful. So yeah, here is a example of a configuration file of Suricata. This is the DPDK part. Here is the PCI address of the NIC we are working with. There are some DPDK parameters, and there is the drop filter. In this example, I have 4 rules. One for matching this specific source IP address, or flow with this specific IPv4 address. Rule with one specific source and destination. There is a range of IP addresses here, and just all the flows that match these protocols. Okay. Also, to measure the performance and verify the functionality of the filter, we wanted to implement some counters that we could extract the number of filtered packets from the flows. We did this with the help of the count action, the RT flow count action. But sadly, it was not supported on I40E, so it supports the I40E supports the drop filter, but we cannot extract the statistics from it. But on the MLX5 and ICE, this functionality is supported. Yeah, but we had one drawback with the ICE, or I can say 2 drawbacks with the ICE PMD, with the count action. Because of the internal working of the ICE PMD, we cannot use masks in the pattern. So each rule has to be one specific flow, and this also reduces the amount of flows we can filter this way. So yes. Here there is a simplified version of a sequence diagram of the process, how rules are loaded and the statistics are extracted. So Suricata is launched, then in the process setup, setup process, the RT flow create is called, all the rules are created in the NIC, and then when Suricata enters the receive loop, and the periodic counter check comes, you can see here that we query each rule and get the statistics of each rule. We accumulate it, and then we update the global Suricata statistics with this. Also, the counters were very useful while developing Suricata CI. It's our test framework for measuring Suricata performance. It's based on PyTests, and we generate the traffic with tracks, traffic generator, and the Suricata receives the traffic. The topology, you can see here, we have a tracks in loopback mode and the switch, and one port of the switch is mirrored to Suricata to receive all the eggs and takes traffic. We did some performance tests on this. They are still in development, but like the early tests showed that on HTTP, HTTPS, and SMB traffic, traffic profile for tracks, when we filtered half of the traffic, we doubled the performance of Suricata. So when we filtered the unwanted flows, it clearly showed that the performance of Suricata was increased. Yes, now about the dynamic bypass, the dynamic filter based on RT flow rules. As I mentioned, the Suricata signatures, or sometimes called rules, can contain in the options part a keyword bypass. This means that the flow is not to be inspected anymore when it's active. Again, usually these flows are some large expected flows from YouTube, Spotify, Netflix, or some encrypted flows, or the flows which an inspected stream that was reached, meaning that they shouldn't be inspected anymore. And the goal, again, of this was reduce load on Suricata by offloading to hardware. Until now, Suricata was doing this bypass in the software, so this was more load on the CPU that we could potentially offload to NIC, to the hardware. Initial idea was to utilize the drop and age actions. Age action basically we can set a specific timeout interval that after that timeout the rule will generate some alert, or we can extract from the rule that okay, the flow has timeouted, the flow that was matched against this rule, but it was only supported on MLX5 from our hardware, so we didn't think this was general enough. We were looking for another solution, and currently, as the dynamic bypass is still work in progress, we are using drop and count actions. Both are supported on MLX5 and ICE, and we are also utilizing a special thread we call a bypass manager to not put more load on the workers, so the bypass manager can manage this, offload these rules and everything around it. And I didn't mention until now that when a flow becomes inactive after some timeout, the corresponding rule, the RT flow rule, is destroyed, so it doesn't take space in the NIC. More about the Suricata threading model we have. There are workers that pull and analyze packets, pull it from the NIC and then analyze them. We have a flow manager that manages the flow table and the state of the flows. And also we have, as I mentioned, the bypass manager that manages the bypass of flows. Here on this diagram you can see how each of these components communicate with each other. Yeah, the workers pull from the NIC, from the queues. We utilize RT ring to send the information about these flows to bypass manager. Also, the workers communicate with a global flow table that keeps the states of the flows. The bypass manager also communicates with the internal flow handler table that we were implementing that basically keeps information about the flows and their corresponding RTE flow rule handlers that are like the opaque handlers that correspond to the rules, and then based on that they can be destroyed, or the rules can be destroyed or queried. And yes, also there is the flow manager that manages the components of the flow table. Sorry. And here you can see the first part that happens in the dynamic bypass. That's the applying or loading the RTE flow rule. When the packets comes to the worker and the flow that is bound to this packet is supposed to be bypassed, the flow is added to the flow table. Then the flow passes, or the worker passes the attributes of this flow to the bypass manager. We utilize also RT mempool and RT ring. The bypass manager then dequeues the needed information about the flow, creates RT flow rule in the NIC. If the rule was created successfully, we then set the flow of the state of the flow to capture bypassed. That means that Suricata doesn't have to worry anymore about the state of the flow because it's bypassed, and we add a entry to the local flow handler table. In the case that the loading is not, or the creation is not successful, maybe because the maximum number of RT flow rules was reached, or some other error happened, we just set the flow back to local bypassed, and we'll let the Suricata handle the bypass. Okay, and the other part of the dynamic bypass is checking the flows and destroying them, and destroying the rules, the corresponding rules. So there is a periodic check of all the bypassed flows, and we for all the flows query the NIC for the filtered packet count, and then you analyze this information in the bypass manager. Then the bypass manager decides, okay, if the packet count was 0, so the flow was inactive, we destroy the rule, so it doesn't take space in the card. We set the flow state to local bypass, so Suricata can handle the bypass by itself, or then delete the flow from the table, or do the appropriate actions. And yes, then we remove the entry from the flow handler table, and repeat this for every bypass flow. Okay, that was everything from me. Thank you for attention, and if you have any questions, you can ask now. Yes?
So when you're offloading the rule, sometimes it's possible to get another packet in between, right?
Yeah.
So I'm guessing that you keep some kind of information that you offloaded the rule and you don't need to track it again, or even if you got this packet, right, inside the Suricata.
Like you mean situation when another packet from the same flow?
Yeah, it's possible that you'll get 2 packets from the same flow.
Yeah. We do it. That's basically the Suricata part that was already there with the worker when it marks the flow as capture, or it's marked as bypassed. Then all the from my understanding, I was not implementing this. It was already in Suricata. All the packets are then from the same flow are bypassed. Like yeah, only the first packet. Is offloaded, or like it goes to the bypass manager, and the bypass manager works only with the first packet from the flow.
And one more question: the bypass manager basically it's a different thread, right?
Yes, it's
maybe I missed something. Okay.
Yeah, sorry, maybe I didn't mention. Yeah, all of these are different threads, and there's the NIC. Okay, thank you. Yes.
You mentioned running into these issues with different rules being needed for different network cards.
Yeah.
Did you just resolve that by basically treating the different network cards differently and coming up with certain rules that work for certain network cards, and that's basically the way you handle it?
Yeah. Like we need to figure the combinations, for example, with RSS, with the right hash functions, or with the right setting up the queues for the receive queues with a different, for example, with a different RT flow rule. Then it sets up the pattern, or like there was many combinations of that we needed to implement. Yeah, but we tried like the core to be the same. Also with the drop filter, we tried to do the filtering part and the statistics part to be independent, or like not to be dependent on it. So like the I40E still can work with the drop filter, but it doesn't count the statistics. Or if I answered your question.
You did. Thank you very much.
Thank you.
Yeah, thank you for showing the limitation you found in the DPDK flow implementation. For sure, there are many limitations depending on drivers, etc. That's probably something we should improve. And the first step to improve that is documentation, for sure. Some work is in progress to improve documentation of the Flow API in implementations. Second step is what you did, I think. You are doing some tests. That's very good. You show the limitation. Maybe you can go a bit further by creating some bug entries. I mean, some limitation cannot be changed if it's not supported in the hardware. Maybe there is no way to implement it. Yeah. But sometimes we can do something like you mentioned. You need two rules for IPv4 and IPv6. Maybe in the driver we can manage that. So I think we could open some bug entries for such limitation and try to remove these limitations.
Okay.
Yeah. Then the next step is to automate the tests. This is what is done currently in the DTS group. So if you're interested, you can join the development of DTS. For remaining, DTS means DPDK Test Suite, and Flow API is starting to be implemented, right, Patrick? Yeah. Yes, that's correct, and you'll talk about it. So yes, for sure, we want to automate testing of the flow implementations, and we will be able to find more limitations. And then maybe a future step could be to have a kind of validation of drivers, show which drivers are following some global common behavior or not, and maybe it's a good incentive for driver developers to remove some limitations. What do you think about it?
I probably didn't catch the meaning of the question. I was listening.
I mean, okay. Yeah. First question is: do you think it's very important for DPDK to remove the limitation we have in some driver implementation regarding the Flow API? Or can you live with these limitations, or do we think we should really work on it?
Like some depends probably on the hardware we are supporting. So because on some it was actually okay, like we didn't run onto almost any limitations, but yeah, maybe just I will maybe just sideway a little bit. A few years back, there was also one group from our company that did a project called RT Flow Checker, and I really liked the idea behind it. It was basically just testing the capabilities of different NICs for RT flow rules, but it's not. I think it's not supported for the new versions of DPDK, and that seemed like a good way to check what is possible. So maybe when not supporting, I don't know, the more capabilities on the hardware or in the DPDK community, as you said, then some checking tool like this to be officially supported, that seems like a nice idea to me.
Yeah, I think the way to have it officially supported is to integrate with DTS. Really.
Okay. I hope I answered your question.
Yeah. I want you to say, yes, it's a big problem, we need to work on it. Just say that.
Okay. Yes, it's a big problem, we need to work on it.
Okay, we'll work on it.
Okay, thank you.
Thank you.
Thank you.
Next we have service chain with hardware acceleration in virtualized environments. So Rony Bar Yanai from the team. Welcome.
Okay, I can start. It's 4 minutes before, so you know. Yeah. Okay. 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 So the today's talk is about service chaining with hardware acceleration in virtualized environment. Before we talk, some credits to the main contributors. The solution is simple, but it was hard to get there, so thank for all those guys for helping. Let's skip the agenda and jump in. Okay, so in the recent years, or let's say the 2 last decades, services moved into the cloud. Okay, and the cloud, in order to do that, it becomes virtualized. Okay, you want to utilize your hardware, save cost, better memory, better network, better everything. It's more dynamic, and it's you need a lot of work to do in order to deploy and to reconnect your network. Side by side with that, there is also what we call VNF. VNF is network function. This is more belongs to the infrastructure of the network, and it's like a gateway or a firewall or a router, things like that. And they had like two steps in the evolution. First step was not working anymore on a dedicated hardware. You just take off-the-shelf hardware with standard NICs, DPDK, and you have this appliance now. And the second one is what they are doing now, which is cloud native. It means that they can run fully virtualized on the cloud. And this is the focus, how we accelerate it. Together with the virtualization came another thing, which is software-defined network. It means that we can we split the network into a centralized controller. The most famous open source is OVN or Oven, and also the data plane, which is separated, and in the community it's used OVS. And there's also standard to configure your network, which is OpenFlow. And this gives a lot of flexibility and a very fast phase in developing a new feature and automation. And this is what most CSPs are doing. Some of them are using open source, but others have the exact same architecture, but they are not using OpenFlow. They have their own proprietary API. Okay, so we have a lot of benefits of doing SDN. But what happened is some of the functionality moved from the switches into the host. You now need to move packets inside the host, and you need to put CPUs in order to do that. Until recently, it was, let's say, okay. But now, let's say 5 years ago, it was 10 gig, but today, or maybe 25 gig. But today, CSPs are putting 200 gig NICs on the host. And in order to move 200 gig, what on a regular workload is about 30 million packets per second. If you're looking on let's say, implementation of switches, virtual switches, the range that of packets per second they can do is about 500,000 to 1.5 million. Sometimes if you do something more optimized, you can do more, but then you lose the flexibility. And it means you need to put like 20 cores or 30 cores on the host, just moving packets. And this is not going to be better, it's going to be worse because bandwidth is increasing. We have now 400 gig and 800 gig for AI workloads. In AI workloads, the packet size is bigger, but usually you can have 8 NICs on the same host. Okay, so in order to maintain the requirement, CPU can no longer do it in software. Okay, we need hardware assistance. So this is example just like the previous talk. You have, in DPDK, you have RTE flow, which you can define pattern and actions. And when the packet is going through the hardware, it will match and do the actions according to the user configuration. It's usually split into two. One is the control path, which means that if the packets that you don't know what to do with, you send it to the software doing processing. For example, if it's Suricata, it's do packet inspection or something. If it's OVS, it decides according to OpenFlow what to do in order to direct the packet to the right place. And then you can configure the hardware. And from that point, all the logical flow, all the following packets will go through the same match and action pattern, and you can get a very high rate. Okay, so this is already implemented in many places. In the obvious, which we couldn't push, I see the obvious guys there, but we have our own obvious implementation that we can get 30 million packets per second with a high scale. Okay, and this is what we already have. I'm taking a firewall as an example, but now customers are coming and they're saying, I want to run also a service. Okay, I have the switch, everything running perfect, 30 million, I'm happy. But now my customers wants to add another services, like firewall. This is one of them. So how it works today they're only using it for the north-south traffic, like going out of the cloud and going back. But now they want it on an east-west. So what it means today, they need to send a packet to the firewall. The firewall is an appliance in their cloud. They need to send the packet to the firewall, get the packet back from the firewall, and then send it again. So they get only a third of the bandwidth they have. Okay, they're wasting 2/3 of the bandwidth. And of course, the scalability issues and load balancing, you need to assign each firewall, each appliance to some host, and it's very difficult to maintain. Okay, so the obvious solution is put the firewall inside the host. Okay, you have a switch. The switch is directing the packet, and now you add just another connection. Instead of sending the packet to the firewall outside, you're sending it to a VM internal to the host with the firewall. The firewall will process the packet, will send it back to the switch, and then you do the other switching and send the packet to the workload, and the other way around. Okay, so this solves the, let's say, the scalability issues and the wire performance issues. But the problem is that we break the hardware acceleration now. Okay, it's no longer fully hardware accelerated because you accelerate from the wire to the firewall, from the firewall to the switch, from the switch to the workload. This is fully accelerated. But the firewall itself, it's now a software only. And we are back to the problem that we cannot provide enough performance to the customers, or we need to put too much cores. And then it's not effective. Back in the DPDK summit, I think Ori Kam did it, right? It was yours, huh? We introduced helping. What is helping? Another problem with this topology that I didn't explain is that on a firewall, you usually work on two virtual functions. It's not like a switch. Okay, you have like two separate virtual functions. Each function has its own domain, and each is configured separately. So with helping, what we can do, we can define a special hardware queue and glue it to a TX queue. So when you get packet on one virtual function, you can say, okay, if this, let's say it's a firewall. If I'm matching this is a 5-tuple, it's approved flow, send it to the RX queue. The RX queue is glued to the TX queue. The packet's coming back in the hardware and appearing in the switch. So you have a full accelerated pipeline in hardware. The packet will not go anymore to software. Okay, so now you have a full path in hardware. Packet going from the wire to the firewall, doing helping, going back to the switch, and then going to the workload. We need to loop it back. But everything is in hardware. This is already exists, and we also have deployments like this. But this is not like the best we can do. Okay, why it's not the best we can do? Because when you have helping, you reschedule the packet. The packet came out of the hardware, and now you put it in a queue. You need to wait for the scheduler to pull it and continue the processing. And then, again, you send it to the VM. It needs to do loopback, and you put it on an RX queue. And again, it should be scheduled and be processed. So we process the packet 3 times. Although the pipeline is the same, okay? Go from this, from port A to the firewall port A, and match city, do a helping, not do a, send to the port. On the switch, you do the switch logic, like VXLAN decap or whatever, and then you can send it to the VM. The pipeline is the same, but we switch the packet direction 3 times, and this is expensive. Another thing is that we introduce another queue now, and if you have another queue, you now started to compete with the queues of the workload. Each VM has its own queues, and now you need to handle priorities. You want the firewall not to block the VM, so it should be higher priority, and it started to get complicated. Okay, so what we can do? So we want to avoid packet direction changes. So the first things that we need to do, we need not to write it in the code. Okay, in RT flow, it was called ingress and egress, but it's TX and RX. You put a table explicitly on one of the directions. So there is no way someone can optimize a thing like that if you tell the hardware, put it here, do helping, and put it there. So we need to get rid of those directions in order to do some optimization. Because if you look in a high level, the direction should be maintained. You have RX to the VM, so it's a pipeline. Switch, firewall, switch, workload, and the other way around. And they're all on the same direction. Okay, so we need to get rid of this RxTX. So what we're going to do, we're going to have what is called local or unified FDB. On the firewall itself, we're going to take all those virtual functions. It's usually 2, but it could be 4 or 8 or how much the customer wants. And we merge them into a switch. Now a packet coming to the virtual function, the first thing it's going to hit is the switch. Like it's an exact copy of the switch below. Packet from each of the uplinks or the VMs or the virtual functions hit the same place. It's the root table of the switch. And from that, you can match from each port you came, and you can do all the processing. You have no longer a direction like egress or ingress. And of course, the RX and TX, those are maintained. If from the switch itself you want to send to the VAF, you still can use RX and TX and Airpin and all of this. Okay, so what we did is we removed the need for a direction. We're working like a switch now. Okay, now how this helps to optimize? Because there is no direction anymore, it's just a switch. When in the switch, a packet came, let's say from port A, the first port, let's call it port A, and I'm telling, I want send it please to port B. Internally, since it's a configuration I did, and I know it's an STD switch on the chip, I can jump directly to the hypervisor switch. I don't need to go through helping queue anymore. I'm just jumping to the switch. Okay. So this is the pipeline. Each color can be implemented by a different company. Okay, the switch can be OVS, open source community. The green firewall of some company, I don't know, Check, Palo Alto, Cisco, whatever. And the workload can be whatever the customer wants. And they don't know about each other. Okay? So you write, you just need now an orchestration that will tell you to do this local FDB on the firewall. And from that point, everything is transparent and without any additional coding of the user. So let's go through this. Packet coming from the wire, okay? First, hit the switch, the hypervisor switch. The hypervisor switch has a rule that tells it, okay, go to the firewall, okay? The firewall that was written by another company and used running on a VM or container, we're using RT flow to configure the hardware acceleration, okay? If it's a firewall, let's say the first few packets will go to software, and then you approve or deny the flow. You configure the connection tracking table you have, and you say either drop or send to the other port. When you send to the other port, because this is a local FDB, it's like a second hierarchy, internally you can jump directly to the FDB. You don't need to move through the scheduler. It's still one-time schedule. Again, the packet will hit the switch, this time from a different port. The switch can do the switch logic, and then send it to the right VM. So we maintain the direction, the entire direction, without flipping the packets anymore. We also made it like modular, that each component can be written separately and by different company, and the only one that should know about it is the orchestration that need to put this local FDB together. Okay, on the TX side, this is the same. Okay, the workload is sending packets to the hypervisor. The hypervisor, the switch will do the switching part, then we send to the firewall. If the firewall approves this packet, it will send it to the wire. No need to change the packet, okay? Now, there's still limitation on that, because each hardware has its own limitation. For example, if you want to encrypt or decrypt, in this case, if you're sending packet from the, I'm talking about here on NVIDIA explicitly, if you're sending packet from the VM, and you are on the TX side, we cannot decrypt. But it also doesn't make sense that the VM will send encrypted packet and you want to decrypt it on the switch. It's always the other way around. And there might be some other limitations, but we work on, this is the only limitation I know about, but we are working on removing them and eliminating the need for direction completely. Okay, now, this was about firewall, but if we think about it, there are VNF that you want to combine few VNF together. You have, like in 5G, you have what is called UPF that can be virtualized, and some of it can be sent to a gateway which can be virtualized. And this topology can work also for let's call it microservice architecture, that you have few services, each one is accelerated. The only thing that you need is to do this local FDB inside, and you need a switch that can direct the packets. Okay, so this is a result. Okay, we did more or less the same. We just eliminated the 2 points of the loopback and hairpin, and this makes the hardware work much better because you schedule the packet once. It's a one-direction runtime. It's more easy to let's say predict performance, less jitter, less latency, work better. And there's the full separation between the workloads. Everything is separated. There is no, I don't know, you don't offload functionality from one side to another. You don't, if you want to encrypt or do firewall, you don't start to add functionality to the switch. You just put a firewall and that's it. So such an architecture can give vendors ability to write their own service with full acceleration, and knowing they can be run as a service in such a topology. Switch, if you look on a VNF, I think I skipped that, but on a single appliance, we also do the hairpin stuff, okay? You have, like, if you take the entire box for doing firewall, you still want to do wire for wire, it works with hairpin, and this is what we do today. But if customers will work on a switch, in this case, it will be, for them it will be the same. You just send from port to port, you just need to put explicitly the hairpin. So they can write the application once with one offload without knowing if they will run as a standalone on the entire box or run as a service. Okay, so hardware pipeline is end-to-end. There is no changing in direction, which means the best latency, the minimal scheduling effort, and the best performance. As I said, firewall is just an example for that. There are other things that could be done: load balancer, encryption, gateway, they're doing NAT, and others. And also in more complicated scenarios, not CSPs that run in cloud, like let's say 5G network, there are multiple VNF that can be run on the same host, and it can communicate with them and get the best performance from the hardware. That's it. Questions?
Thank you for the presentation. Something I don't understand. What you presented is something that is already available, or is it something that...
We are pushing it upstream. It requires also kernel, because you need to merge virtual functions together. We are pushing it upstream. It will be in the next year, I believe.
Okay, thank you.
Is there any dependency on a type of NIC, like CX6, CX7, or support will be generic?
From ConnectX 6, we can support it. It depends on hardware steering.
Sorry, can you please reiterate on the point what's the main change between the loopback solution and the new variant?
Yeah. This is like a bit of a history, because when you have like appliance, like a firewall, you're bumping the wire. You get a packet from one side, public and private, and you send to the other side. And the solution for that, and you're running on 2 ports, virtual functions, usually, okay? And the solution for that with RT flow is putting rules on ingress or egress and moving using hairpin, which was a revolution back 6 years ago, from side to side. But when you're doing that, it means that you reschedule the packet. Okay, you got out of the hardware on the RX, and now you schedule TX. It's similar like someone send a packet from one of the virtual functions. And this costs performance. Now, if you're doing it as a standalone, you're bumping the wire, there is no cost, because this is the best the hardware can do. But if you are not alone on the host, there are others, like a switch, you're now starting to flip the packet back and forth per direction, because once you did the hairpin and you're going back to the switch, you want to send it to the workload. Now you're in direction of going out to the wire. So you need, we do it internally, okay, it's loop back, but you flip the packet again and you reschedule it. So now you have 3 packets instead of 1 from a hardware perspective. And in order to get rid of that, first you need to get rid of the syntax of the terminology. You cannot put this on the egress and put this on the ingress and do hairpin, because we cannot optimize. We will do what you want. Instead of that, you work also a switch. You are no longer, let's take a simple use case, you have 2 virtual functions. Instead of now offloading a rule to ingress, egress, you merge them together into a switch, and you put only rules on the switch where there's only egress in switch. One direction, okay? And then, internally, we can do those jumps. Okay, when you tell us send a packet down to the switch, you don't need to do hairpin. We just, internally, we switch domain and jump to the root table of the switch, okay?
Okay, thank you.
Sorry, can you explain that again? It's not going to the firewall? A switch does the firewall functionality? I did not get that part.
I can't hear.
Questions over there too. Did you use it?
I didn't hear the question, sorry.
Okay.
Can you hear me now?
Yeah, but...
Yeah. So can you explain that again, what you were explaining? When it goes to the switch, how does it go back to the firewall for firewall functionality?
You mean this slide?
No, the next slide, right? The next slide. Next. Yeah, here.
Here?
Yes.
You're working on a switch. If you're working on a switch, there is no direction. Everything is egress, I think, or ingress, one of them. Egress? Okay. It's there is no like a direction of domains. Okay, there is one. So you don't need any more to also create helping queues, because when you in a switch, when you tell let's go with uplinks. If you got from one uplink and you want to go to the second uplink, you don't need to do anything specifically. Okay, we just send it to the wire. And this is not like virtual functions when you must use helping.
Hi. With your solution, are you able to minimize the DMA bandwidth or the PCI bandwidth?
You don't have PCI bandwidth. You also reduce the PCI.
So the VNFs are the workload VNF and the firewall VNF are on the host. So it must be going through the PCI, right?
No, the packet is in hardware. Only PCI bandwidth that you need is if you have like big tables and you need to have memory, you have cache misses, you need to bring memory. So it's everything. It's one hardware. Just you have isolation. You have what we call Gavami. You have a domain of isolation that you can jump between them. It's not going through the PCI.
So the packet is being delivered to all the VNF sites. So in the service function chaining, if there are 3 VNFs are there, you are going to deliver the packet to all the 3 virtual functions, right? So some penalty is happening, right, somewhere, either the DMA or the PCI.
No, PCI is only when you send packet to software, and in this case it will be the last one, right? The workload. In this case, where it is, yeah, the workload. Only on the workload it will go through the PCI. We also use PCI to bring memory. If you have like a very large amount of rows in the hardware and it doesn't fit in the NIC cache, then we have cache miss and then you use the PCI to get the memory. Okay, but the packet on the PCI only goes to the workload in this case, and that's it, and from the workload.
Okay.
Thank you.
Okay.
So now we got a bit of a break, and we'll be back at 3:40 p.m. local time with Lucas. I'm going to mispronounce this. Lucas Kikeli from Dyna NIC. We'll see you back then.
Good afternoon, everyone. Nice to see you here. My name is Lukas. I'm CTO of a company called dynamic. We are a growing Czech company. We focus on FPGAs, we focus on smartNICs, and hardware acceleration of network processing. I would like to speak today about a topic, a more general topic than maybe other speakers before me. I want to speak about an idea how to specialize, or how you can specialize your RT flow groups to fit your application instead of relying what is available on the smartNIC. You can specialize to what you need, and I think, or I believe that FPGAs or FPGA-based smartNICs are the way that can enable this kind of approach or this development philosophy. So my agenda is not to sell you our product. My agenda is to give you an overview of the NIC market, or of the smartNIC market, of the edge computing. So what Ethernet adapters are available for servers, and to give you an idea or my understanding how this sector of the market can operate and how DPDK or RT flow can be used to really deliver the acceleration that is required by applications. Some speakers already touched to some points that I want to make today. For example, 2 presentations ago, Adam was talking about how he had a problem with different FPGA or different ASIC cards supporting different RT flow rules. This is exactly the key point that I will try to make throughout my presentation, how to avoid this kind of problem. So to start the presentation, I believe that it is generally known that the world always needs more connections and more networking. Since the start of Ethernet, or start of the Internet or networks in general in the 80s, we see a steady increase in interface speeds throughout the years. So each few years we double or triple, or n times increase the performance of the individual network ports. And of course the Ethernet adapters have to keep up. For the Ethernet adapters, we are usually 1 generation behind. So right now, I think last year, standard for 800 gigabit Ethernet was finalized. Right now, we are seeing Ethernet adapters with 400 gigabit Ethernets that have been created or developed a few years ago, but only right now they are entering the market in bigger numbers. So the demand is 1 generation behind, but the demand is still growing. So this is not only my idea, but also Del Oro, like a big company that monitors, among other things, also the Ethernet adapter deployment. They expect that the growth for usage of Ethernet adapters of this whole market will be around 27% annually, and it will exceed 16 billion by 2028. So they have to actually revise their earlier forecast of the market. They a year ago or 2 years ago, they only expected a growth of 10 or 15%, but with current driver of backend connectivity using also Ethernet instead of InfiniBand or other technologies, so more and more developers of AI clusters rely on Ethernet or on Ethernet adapters or network interface cards to be able to enable connectivity in their AI clusters with GPUs. So based on this driver, they have to increase the growth estimate. And also another estimate that they have is that 400 gigabit technology is now being developed in larger numbers, and by 2027, 10% of newly deployed servers with Ethernet connectivity will have 400 gigabit Ethernet ports. This shift in performance, so going to higher and higher speeds, have some other changes linked with it. So in recent years, in last 10 years maybe, we see a clear trend of shifting from a common NIC, so from a common network interface card that basically receives the packets, to a more advanced or smarter NIC, which can give you some additional features. So this trend is not only visible for a few years, but it is actually growing. So each year, more and more smarter NICs are deployed compared to the standard or common network interface cards. So the advanced features seems like a requirement for higher speed. So if you are operating at 100 gigs, if you are operating at 400 gigs, a NIC is not enough. Even with today CPUs with many cores, you still need some push, some advanced features handled by the card itself to be able to handle traffic on this kind of speeds. So the focus is growing, and the focus is on the more programmability on the network interface card level. So what is so smart about the NIC? So the basic difference, as I mentioned, the standard NIC is basically you have a traffic, you have a optical link, which have two directions, input and output, ingress, egress. And then you have the Ethernet and serial implementation, so the lowest level of the Ethernet. And then you just send the package through DMI to the host computer or to the host server. With smarter NICs, you add additional accelerators or additional functionality. There are different levels of smartness or different levels of acceleration. Someone calls them offload NICs, which offer like basic functionality, some checksum computing, some TCP offloading, or other features. More sophisticated or more complex offloading. Now the NIC is called smartNIC because it offers more, it is more smart, let's say. And usually there you have some programmable pipeline with packet parser, with filters, with different queues, and even some domain-specific acceleration units. For example, it was mentioned in previous presentation, you can have pattern matching or other engines there. So just to summarize, the smart NICs usually offer some kind of traffic processing pipeline directly on the network card level, which can process or accelerate some selected network protocols or selected network stack operations to filter interesting traffic. So only interesting traffic will go to the host computer, and the card itself can deal with the bulk traffic or bulk operations that are not really that interested or that important for the target application. Usually what the smartNIC can do is some kind of encapsulation or decapsulation of tunnels, some kind of encryption and decryption of payloads, or even some application-specific use cases or application-specific operations on per packet basis. So as an example, there was the pattern matching example. Also an important feature for some application or for many is some kind of stateful processing, so some level of connection tracking, where you can not just offload the connection, not just offload a filtering rule, but you also want to keep track of what is actually going on with the offloaded connection. So these are the basic features of this, what can smartNIC give you. Key benefits for the application and services. So thanks to these features on the card level, we can basically pre-process or post-process some incoming or outgoing data, so the CPU does not have to do all the work on each packet. Less CPU cycles are spent per packet, and you have more. You can process more packets. Basically, you are offloading the networking-related operations to the smartNIC. So this is something similar, like was presented by Lucas this morning with the Suricata acceleration, with the acceleration of pattern matching. He was able to offload the pattern matching part of the processing, saving some CPUs for the core functionality of or for the rest of the Suricata functionality. Complete offload is another concept or another approach how to accelerate. So you basically offload the mundane task from the server or mundane packets from the server entirely. So the overall performance is increased. You can achieve the same performance using less servers, or you can achieve a better performance with the same number of servers. And you enable basically faster networks or faster services. This is an example like it was mentioned, I think, by Adam, where he was doing some kind of offloading through RT flow. He was able to bypass some packets from Suricata entirely, so Suricata don't need to see all the packets, and it will not change the result that it is able to do its job. So this is the complete offload of some of the packets, complete bypass of packet processing from CPUs. The other benefit for application, some of the applications are very latency dependent. So when we optimize the network pipeline, some of the packets can be directly decided by the card itself, so we reduce the latency, and this can help to lower the response time. It can get faster, and in some special applications like AI training, it can lead to higher utilization of other accelerators that are available on the host server. So for example, if you have a GPUs, multiple GPUs in a server, and you want to train or infer some AI heavy workloads, you need to utilize those GPUs, you need to provide them data in a reliable manner. But if you don't have a good networking connection or good networking interface card, you are basically not using the GPU to the full potential, because it needs to wait for another bit of data. When it gets the results for the current bit of data, it needs to transfer the results, and it's again waiting for the NIC, waiting for the networking communication. So optimizing the networking pipeline can reduce the latency and can increase the performance that you get, or the utilization that you get from another accelerators available on your server. So the idea of offloading some of the functionality to the card itself is not new. DPDK support is already there through the general flow API that is also known or used to be called RT flow. It is still called like this in the code, so all the functions have the RT flow prefix. So many NICs or smartNICs support DPDK on the data path level, so you can receive or transmit data through queues or through MBUFs. But using the general flow API or RT flow, you can also define or control the control path of the smartNIC or of the networking path itself. So you can configure the card to match traffic and perform various actions on the traffic itself with accordance to the rules delivered by the software application. So the matching process defined by the general flow API is divided into individual group of rules, where similar rules should be linked together in a single group, and this group can be linked together with jump actions or similar features of the general flow API. Each flow rule defines attributes, patterns, and list of actions. It was already described on few presentations already. So just a quick recapitulation. So flow rule can be created for a certain port number, for a certain group number, for a certain direction. And the interesting part is the pattern, so basically a key according to which the incoming packets are matched. So in this example, we have IPv4 destination IP address set to a specific number. And then the matching packets, an action should be applied on them. The action can be some fate, so how to forward the packets, or it can be some processing of the packets or other feature, other useful action that can be done on the packet. So the RT flow API in the DPDK specification is kept as general as possible. It supports many actions, many patterns, many combinations of all of these features. It supports different attributes, different parameters, and so on. So it's general enough to be able to support all the application, all the use cases, and to be able to cover all the available hardware. But the other way how to look at this is there is no single card that can support all of the features. So when you are looking for a smartNIC to accelerate your application, you must look at the level of support that a specific vendor is providing you. Again, this was mentioned in previous presentations. There was a discussion about this exact topic. So the support in various smartNICs is different for different PMD drivers in terms of RT flow features, patterns, actions, and other features. So each vendor has a different limitation, and there are actually different levels of smartness on the smartNIC level. So depending on which kind of smartNIC are you using or which kind of smartNIC are you looking at, there can be some different limitations. I divided the cards into three basic groups. So you have ASIC-based cards, you have ARM or CPU or network processor-based cards, and then you have the FPGA-based cards. So basically the ASIC-based, these should be the most powerful ones with most performance, but the problem there is they have fixed pipelines. So they support fixed number or fixed groups, fixed functionality, and if you want to do something specific that is going beyond what is supported or what is in the fast path in the ASIC, then it is not possible, or you will quickly lose the performance advantage. The ARM-based cards are on the other side of the spectrum. Some of them can be accelerated with specific accelerators, but basically they are using an army of CPUs to handle the task, so they are limited by number of packets that they can usually process. So MPPS, millions of packets per second, they have some kind of ceiling, and for short packets, this will reduce the overall performance in terms of gigabits per second. So you are, on one hand, limited by the number of packets that you can do with CPUs, and you are also, the performance is reduced with the complexity of the task. So usually you are not as limited as with ASIC-based cards in terms of what is available on the card, what can be programmed, what parts of RTE flow can be supported. But adding more tables or adding more rules that are active on the card will reduce the overall performance. Again, this is nothing new. This was presented, I think, a few years ago by similar presentations, and it was also mentioned that there are some applications available that can test not only the feature set but also the performance of various cards under various loads or configurations. So the last group that I want to focus on today is the FPGA-based cards. Their main advantage is that they can be reprogrammed on demand. And you are actually programming the high-performance pipeline, so you can achieve the similar performance as ASIC-based cards because you are directly programming the high-performance pipeline in the FPGA chip. You are programming it as a hardware acceleration pipeline, so it can retain wire speed performance and other performance features. You can customize the pipeline through reprogramming, so you can, if you need something specific, you can program it. If there is a new protocol tomorrow, you can reprogram your packet parser to be able to support this new protocol. So the flexibility of the FPGA cards seems to be the key benefit, and its value is growing in time. As I mentioned at the beginning of my presentation, there is more and more focus on programmability and advanced features in the smartNICs, and I believe that in the future this trend will only continue. And the unique feature of the FPGA card, that they can be reprogrammed during their lifetime, I think this will give them additional value over time. And with the current trend, they will be more and more prominent in this market. So in various use cases, you usually have different requirements. It can be you need different patterns or different keys. So for some, you are good enough with L3, layer 3 identifiers like IP addresses. For others, you need L4 identifiers. For some use cases, you need completely specific identifiers like for UPF, you need specific header or specific tunnel to be able to be parsed, and you need to extract some ID from the tunnel to be part of the matching or part of the pattern in the table. Also, for different use cases, you need different capacities of the tables, you need different tables, and so on. And because of the evolving network landscape, you cannot actually tell what will be next or what will be required tomorrow. So you need an ability to be able to add currently unknown headers in the future. And as I mentioned, currently the main driver is AI for network interface cards, at least, and this requires a whole new set of protocols. So we have RDMA, we have RoCE2, or other protocols. So in the future, maybe in 2 years, there will be another different driver, and the NICs would have to be able to accommodate this new opportunity, would need to be able to address this new market. Another key feature that I also see in our operation is for some customer, it is interesting to have switchable interface speeds for future growth. So basically they want to buy card today with their current 100 gigabit networks or 100 gigabit links that can operate on these links. And without buying a new card in 2 years, they want to be able to switch to 400 gigabit links. So with FPGA smartNICs, this is also a feature that is available. Basically, you will change just the configuration of the MAC layer of the FPGA, and you can switch from 100 gigabit Ethernet card to a 400 gigabit Ethernet card on the current FPGAs. And I think that also the important part that speaks why the FPGA cards are the future is number of companies that are able to create not only the FPGA chips, but also the FPGA cards. So there are multiple companies in the US, in the Europe, and in the Asian market that are active and that are developing and creating and bringing new and new FPGA cards to the market. So on the FPGA card, the FPGA chip itself is reprogrammable. All you need to do is provide your own packet processing pipeline. This pipeline usually have some defined architecture. You can see it here on the slide. So on one side you usually have Ethernet MAC. These MACs are provided by the FPGA vendors. On the other hand, you have PCI Express connection to be able to communicate with the host server. Again, these are IP cores provided by the FPGA chip vendor itself. And all you need to do is program the pipeline in the middle. So the processing of the packets. Usually you start with some packet parser. Because it is reprogrammable, you can program some protocol stack, and you can, in the future, you can add more and more protocols into this parser. Then you have a pipeline of packet filters or rejection tables or RT flow groups, however you want to call them. They basically take the parsed information from the packet, look into a table or look into a group of rules, and select an appropriate action to be executed on the packet. Then you can execute the action on the packet, and you can forward it either through DMA engine to the host computer, or you can drop it or forward it back to the interface, to the Ethernet. So this general implementation can be is what is used on the FPGAs, and it can be reprogrammed in the future, or you can start with one pipeline and then change it according to your evolving needs. So you can add different packet filters, you can add additional protocols in the packet parser, you can change the set of actions that are supported on the packets, and so on. So all of this is possible with the FPGA cards. So my main point that I want to give with this presentation is change the philosophy of the software development. Do not use what is available on the smartNICs, but select what you need. And with FPGA smartNICs, this is possible. So you don't, if you have an application that you want to accelerate, that you want to bypass some of the flows, that you want to offload some processing into the card itself, with ASICs, you have to look at available models on the market, and you have to see like which model supports which kind of functionality. And then you have to choose a card that best fits your use case. With FPGA smartNICs, you can directly say like, I want these features, I want these specific RT flow groups, and you can just reprogram the pipeline in the FPGA to actually deliver you exactly what you need. So you can better accelerate your applications, you can have the groups or the actions that you need, and you can get the best performance boost achievable. Of course, when you are customizing your flow groups, it's better to be more specific. So if you actually use this approach, you can argue that ASICs can always do like a generalized version where everything will be a TCAM matching. They will have 10 groups with I don't know how many rules. But this is actually costly in terms of resources. So optimizing the rules or optimizing the tables to your needs is actually efficient from the point of view of the resources, and you can get higher capacity of the tables, and you can basically squeeze more from the FPGA card or from the smartNIC itself. So just to illustrate, with some current FPGA cards equipped with current or last generation of Altera-based FPGAs. Similar numbers are, of course, achievable with AMD as well. But just to showcase you, I choose Altera. Starting from the left, we have the older Agilex F series. In the middle is the current Agilex I. And on the right is the latest Agilex M series that is becoming available this year. So with this kind of FPGA cards, you can achieve thousands of TCAM rules, or you can achieve hundreds of thousands, or even up to 1 million of LPM or exact match rules in the FPGA itself. Of course, you can achieve additional flow connection tracking rules in the memories that are available on the cards, being it DDR or HBM or similar memories. So the last point that I want to make is that all this maybe seems so nice to be true, but of course nothing is for free. So the only problem, or the main problem that usually is seen with the FPGA smartNIC is that the FPGA programming itself, so the creation of the pipeline that I described, is very hard. But with current technologies, it doesn't have to be. So compared to the standard approach with RTL or with HLS, where you basically have to have a specific dedicated team of developers that know how the hardware works, with current technologies like P4, which is still not the ideal solution, but it can be used for rapid prototyping, and it can be utilized by software developers to specify how the FPGA or other pipelines in the hardware should operate with packets. You also have a solution where you have a turnkey FPGA bitstream that can be delivered and customized according to your needs. And that's exactly the message that we want to bring and that we want to provide with our solution. So we can deliver the bitstream, or we can deliver the acceleration pipeline according to the requirements of specific applications. That's all from me. So in conclusion, the advanced or smartNIC is growing. The offload is inevitable, or the programmability of the smartNIC is more and more prominent. It can be accessible through RTFlow API in the DPDK. However, there are various levels of support in terms of performance in the available cards, but the most flexibility can be achieved by the FPGAs, and the difficulty of the FPGA programming can be avoided by different means. So that's all from me. Thank you for your attention, and I'm looking forward to questions.
Test. Okay. So maybe I missed something. Except programming the FPGA itself with code, which is obvious you need to do, but the RT flow itself is the generic. Each PMD implements its own logic, right? So if you're programming, you also need to write your own driver for DPDK. Am I mistaken in something?
Yes, yes. So if you are building your own FPGA pipeline, you of course have to program the pipeline itself in the FPGA, and also you have to program your own PMD driver. But with some approaches like the P4, I believe that they have like some kind of PMD driver already. Or with our solution, we will deliver the PMD driver together with the customized pipeline. So you can view the solution with the FPGA cards. If you have the knowledge and if you have the team, you can program your own pipeline, your own PMD driver and everything. If you don't, you can employ a solution where this will be provided, and you can look at you can look at the FPGA card even as a ASIC card. You just tell what the pipeline will be.
Yep. I suppose it's possible to upstream a driver for FPGA NIC. We just need the PCI ID.
Yes,
if you change the interface of your NIC, you need to change the PCI ID.
For FPGA cards, there is actually an open source project that we are supporting, which is upstream in DPDK and which can support some of the FPGA cards that we are working with. So parts of the PMD driver are upstreamed in the DPDK.
In NFB?
Sorry?
NFB?
Yes. Yes, in the upstream version, there is no RTE flow support, but in our custom branch, there is RTE flow support. So hopefully in a few months or years, we will upstream it as well.
Okay, but I really would like to have your opinion about the feasibility. Do you register some PCI ID when you change the interface of the NIC with a new bitstream? You see what I mean?
We do not change.
You have only one PCI ID?
Well, depends. There are multiple, at least as I see it, there are multiple identifiers for PCI Express cards, so we will change the project name and project number, but we won't change like a device ID.
Yeah, so when we change the bitstream, it doesn't change the PCI ID.
Yes.
That's probably the issue for upstreaming. How can we know? Because you know, when we probe, when a driver is probing the hardware,
yes,
it needs to know how to adapt to the bitstream.
Yes.
So we need a way to query which is the bitstream.
Yes. So the driver can read the configuration from the card or from the ID.
Mm. It's the other way around.
Sorry?
That's the other way around. You modify the bitstream from the driver.
No, we provide the bitstream and the driver, and the driver sees the bitstream from the group that we support, and it can ask the bitstream about its configuration.
Mm. Okay. Okay, good. Any other question?
I appreciate the advantages of the FPGA approach. Do you have any numbers on the power cost of FPGA smartNIC compared to basically equivalent performance of a non-FPGA smartNIC?
So I don't have exact numbers with me, but I believe that the power consumption is not much different. It again depends with what kind of other smartNIC we are comparing to, and under what load and with what application. So on the FPGAs, we are basically scaling with complexity, we are scaling the number of, or the area of the FPGA that is used. So the power consumption will go up if we have more tables and so on. I assume that with ARM-based cards, the power consumption will scale with traffic and similar features. So it really depends on the workload, I would say.
No, I appreciate, absolutely. But I'm asking about like for like. So if you put the same processing on two cards with the same workload.
Yes, so
do you have an idea of? I'll take order of magnitude. I don't require, precision to.
I don't expect orders of magnitude difference. There will be a difference, like I don't know. The transceivers themselves usually use like tens of watts of power. So the FPGA can use 100 or 200 watts. The ASIC, I don't know, can use 50 or something like that. So it will not be like 10 times more. It will be like 2-3 times maybe.
Thanks.
So why you say the flexibility is more with smartNIC? Because if it goes to the ARM core, right, then it's a flexibility, right? Otherwise, so if we consider Octeon, all these things are implemented in hardware, right? So like the full RTFlow is implemented in hardware. So there's no case where it goes to ARM core and does it. So if there are some crazy thing like VXLAN tunneling or something, then it may use CPU, but all the normal stuff is already implemented in hardware.
Yeah. Yeah, that's the point that I want that I try to make. Like, if you do the standard stuff, the ASICs or the ARM core cards are better because they can do the standard stuff really fast and really good. They are optimized for that. But I mean, in 2 years, the standard stuff can be different as today. So either you need to buy a new card with every change of the networking, or if you want to do something specific, you have a problem. And that's where I think that smartNICs are better, because you can adapt even for something new or something specific.
Yeah. So yeah, if you have a new protocol, yes, Yeah. Some extent, this also has hardware parsers. So it does not need to change the full software. So packet parsing, actually it's offloaded to hardware. So it's a software-defined networking. So we don't need to replace the card for understanding new protocol.
Yeah, but
sometimes
usually,
actions, yes. Like
usually, even if you have a configurable parser or configurable tables, like was the case with Tofino and similar technologies, usually you have some limits. So you cannot have more than a number of tables. You can certainly change the parser, but as soon as you try to do something specific in the parsing, you can,
Yeah, there is a limit everywhere, even if it is FPGA also there is a limit. Yeah, but yeah, I got your point. Okay, thanks. Anyone else?
So you can update the bitstream runtime?
With the FPGA cards, you can update the bitstream anytime you want. Like it's not like you can update it like 10 times a second, but you can update it like every week or every month.
So it's
no problem.
So it's just tied to what FPGA vendor you're using, correct?
Sorry?
I mean, what I'm saying is that we're talking about building a driver, right, for each, yeah. So you need to build a PMD driver for each different FPGA vendor. Is that correct?
No. We actually support, I'm not sure on which slide I have it. We actually support, we actually support cards from all of these vendors, and we support them with the same driver. So we have an abstraction layer in our firmware where we abstract from the FPGA specific part, and the card behaves the same from the software API point of view. So you have the same DMA transfers going to the host computer. You have the same functionality or the same operations, same functions that you can call on top of the card. Of course, in the backend or in our firmware, we have to do something different for different FPGA vendors. But from the point of view of the software application or from the point of view of the API, from the driver itself, it looks like the same card.
Okay, so essentially you can also program the runtime. So everything is same, like the vendor is the same.
Yeah, so if you write
different products, right, different features that you want, you can change it the bitstream and based on some control application and then push the bitstream. So how the bitstream is delivered currently? What's the?
Yeah, so if we are speaking in general, for FPGA cards, there are tools provided by chip vendors that can create a bitstream for you. So you would have to program it yourself. But with our solution, we provide the bitstream for the customers. So basically, we'll provide you a bitstream that can run on a specific card. If you want to switch to a different vendor, you will get a bitstream for a different vendor's card. If you want additional table, we will change the RTL on our end, and we will provide you with a bitstream that suddenly have a new group visible from the RT flow. So any changes to the bitstream that you need, we will handle. And from the point of view of the API, you can have the one application that basically, use DPDK to access or send packets, use RT flow to instruct or populate the filters, the groups in the card. And if you run it on, I don't know, Silicon card, or if you run it on Bitware card with our firmware, you will get the same results basically, or it will work on both cards. Of course, if the card has 100 gig interfaces, the performance will be 100 gig. If you have a Silicon card with 400 gig interfaces with PCI Express, you will get different performance, but the control or the actions that you will do, the behavior of the card will be the same.
So development flow is something like customer says, I need so-and-so patterns and so much of actions.
Yes.
So you give it to them, give to you, right? Then you write the RTL and give the bitstream.
Yeah. Okay. So this is the idea with FPGA cards. You can have this kind of discussion like, I want this type of groups, and either you implement them in P4, either you have your own FPGA guys that will implement an RTL bitstream for you, or you use a company like us that will deliver the bitstream for you.
Got it, yeah.
Thank you. We are running out of time, so I propose we go to the next talk and we can discuss that.
So, hi everyone. My name is Shobhi Jain, and I'm working as a software engineer in Intel Corporation. And today I have Timothy Miskell, one of my colleague, who has joined us virtually. Maybe Tim, do you want to say a quick hello to everyone?
Yep. Hey everybody. Hopefully everybody can hear me. This is Tim Miskell from Intel, software architect here.
Yeah, so today we will be presenting on the topic that is deep dive into the protocol agnostic filter technology on Ethernet adapter with DPDK. I know it's a long title, but the core of this talk will be around, we will be basically talking about the protocol agnostic filter technology. And again, I know it will be the third time in a row that you will be hearing about the generic flow, especially the RT flow. But in our presentation, we will be mainly concentrating on the raw pattern within the generic flow. So maybe we will start. So we have a kind of full agenda. So we will be talking about the problem statement, and in the problem statement, it will be mainly what Lucas has already talked in his presentation. So I think so we should have collaborated for our presentation, Lucas. So we will be talking about the problems we faced when we talk about the Ethernet adapter, and then some of the possible solution. And one of the possible solution is what Lucas has already talked again, that is smartNICs. And on top of that, we have again one more approach, that is a raw pattern, which we can configure on top of RT flows that we will be talking about in details. And also, we will be going through the Arista L2 timestamp as a use case in order to explain how someone can configure this whole raw pattern. So, talking about the problem statements. So, if we see things from the Ethernet adapter perspective, what are the main problems which we see? First of all is the reduced system performance. So like in high performance networking environment, when we talk about telecom data centers, like high throughput and the low latency, I think so we all are from here, the like networking background, and apologies if it is something you all already familiar with, but just wanted to bring everyone on the same page, so that's why I'm talking about these problem statements. So yeah, high throughput and low latency, this is the bread and butter for all the network software engineers. But when we talk about, when we see things from the like a network adapter perspective, and especially from the flow classification perspective, so like if there is no proper mechanism in place for the flow classification, it actually affects the overall performance of your system. Next is system flexibility. So like different applications requires like different classification flows, and also like they need like different type of traffic that needs to be classified. So if we don't have an efficient mechanism in place, it can be really slow and complex, and also like we won't be able, it is not flexible, so we won't be able to actually we won't be able to classify larger number of packets, or like different type of packets. And complex and slow flow classification. So the point which I was saying just now, that like if there is no proper mechanism, a flow classification mechanism there, so in that case the classification can be slow and complex. And The next problem is difficulty in hardware offloading and integration. So like if there is, if the hardware doesn't support proper flow classification mechanism, then the software won't be able to offload those flows on the hardware. And the last is inefficient packet processing. Obviously, this if your hardware doesn't support processing of the packets or processing of the flows, then you have to do everything on the CPU, and it will actually affect your line rate. So all the problems which we have talked about here now, there is one solution for that. That is the programmable NIC with programmable packet processing pipeline, which Lucas have already talked about a lot. Few examples are here. It's like Intel Ethernet adapters, which is like 700 series, which we call as like 412, and also like 800 series, which we call as Columbia-Ville. Also like Tofino switch, so the switch which has P4 programmable switch, and also NVIDIA Connect 6 and Connect 7, and also like Cisco Silicon. And there is a long list of the Ethernet adapters who actually provides programmable like a packet processing pipeline. So these packet processing pipelines actually offers significant advantage in terms of flexibility, performance, and customization. But their biggest challenge is in the complexity in programming and development of the driver. So because now driver has to actually support the parser capability for all of them. And that's where actually the protocol agnostic flow offloading method, named as a generic flow also, becomes helpful. So what happens, the generic flow enabled driver actually learns the network adapter's hardware at runtime and translates the flow offloading request to the specific hardware configure commands. And this learning mechanism actually keep the driver unchanged even though the hardware has been reconfigured. So if we take an example of like Intel Columbia-Ville, like that is Intel Ethernet 800 series. So like that particular adapter, Ethernet adapter, with the help of its like dynamic device personalization profile, which we call as a DDP, which is very specific to this particular Ethernet adapter, but like it can be like if any other adapter which has something similar capabilities can also actually support configuration of the generic flow. So again, the advantage of the generic flow methods, Lucas and Adam have already in their presentation covered a few of these things. So I won't be going much in the detail, just like a quick. So now the efficient packet processing, because now you are not like, now you can offload your like flows on the hardware, and so you can so your line rates, so you have a better line rate here, and more flexibility, because now like as new protocols are developed, like a protocol agnostic system can handle them without hardware or driver upgrade. Improved system performance, so it is linked to my point above, that is it removes the requirement for CPU cores on the host to perform the classification and the load balancing of the packets. So it helps in increasing the packet throughput and reduce the packet latency. And also the deep packet visibility, because generic flow can help inspecting and acting on the inner headers or the payload, and enables advanced use case like deep packet inspection, QoS, and the security filtering. And the last one is the ease in hardware offloading and the integration. So now the hardware can actually offload those easily, and also like there is no hardware specific limitation here. Going a little bit into the how this generic flow offloading is being, so in the DPDK, in the DPDK, this generic flow offloading is being enabled by RT flow. And this slide, I think the content of this slide, you might already be familiar, because again, Adam already covered that what are the few of the functions in the RT flow API which helps us enable this functionality. So like if application, when an application wants to create a flow, so the RT flow create functions get called. It actually then defined some of the components, theirs, and their attributes, pattern, and actions. Then once the flow creation has been done, then the RT flow validate happens, that NIC checks that if it actually supports that particular flow creation rules or not, and if it is, then the rule gets installed in the NIC. It's again, so like what happens that RT flow has a set of predefined data structure which represent the protocol headers with the field that follows, that mainly follows the industry specs. From a driver's perspective, it is supposed to provide a parser to translate the RT flow format protocol combination into the hardware configuration. So like this is how from RT flow side of things works, that there will be a, like the packet will arrive with a certain protocol combination. Then the flow table will be checked for that if there is any associated pattern there in the flow table which matches with the packet. So it's kind of like it checks whether the attributes, whether it's an ingress traffic, egress traffic, and what's the priority of the traffic. Then it goes in the pattern items to check, match the items. If the pattern item match, it performs the associated actions, and it can be any actions like drop or send the traffic to the certain queue. If not, then it performs the default action, and the default action could be that drop the packet or send it into the particular queue so that it can be inspected further. But here, like I said, like RT flow has a set of predefined data structure. But what if we want to support a new protocol that actually like have a new data structure? In that case, there will we need a new data structure in the RT flow. And since the driver parser cover the limited cases, then the new parser logic would be needed to be added to support the new packet types, even if the protocol exists. And that's where actually the protocol agnostic offloading helps. So it is a DPDK feature which actually so in RT flow there is a raw pattern type which you can use in order to actually enable that. So how the raw pattern type works in the RT flow. So again, the flow remains same. If you see, there is only a new block added, that is a raw pattern match. So in this case, when I say raw pattern match, is like if suppose user wants to do a flow classification on the basis of any like arbitrary value. So I will be explaining in the next slide with an Arista like a use case where they wanted to hash on the basis of the timestamps value. And in that case, that is where their raw pattern actually helped them. So in that case, they didn't need to like rewrite the whole driver in order to support that particular flow or that particular pattern. They just used the raw pattern, and they were actually able to hash on the value of that. So how the flow now looks like? So now the pattern arrive. Now if you see the difference from the previous slides to here, so now the only thing is now here the raw pattern is used instead of the pattern. And in the raw pattern there are two things which we mainly consider, is the spec and the mask. In the specs, it's like the value to match, and the mask are the offsets or the value on which the user wants to actually do the like hashing. So packet arrives, again same things happens. It will check if there is any like a associated flow. So it will check for any ingress, like what's attributes, then it will go for the exact match pattern. If it doesn't find any exact match pattern, then it will check that if there is any associated raw pattern matches there, and in there it actually will check for the spec. And last is also kind of an attribute. It's like an upper bound for an inclusive range with corresponding field in spec. And mask is the bit mask applied to both spec and last, and the purpose of this mask is to distinguish the values that should be taken into the account, or we can like partially mask them out. So yeah, so then it will like if there is no raw pattern match happens, then it will perform the default action. If it does, then it performs the associated action. So now moving on to the like, so sometimes like it is difficult to understand that, okay, how this whole thing is working. So we thought of taking this an example, explaining it with an example, and that is the Arista L2 timestamp. Like I said, in the Arista use case, what they wanted to hash on the basis of the timestamp value. And so this is kind of a packet, like a format which they had. And if you see in here, basically, like there are some color coding happening here. So we have source in the blue, it is the source MAC address. In the destination, in the green, it is the destination MAC address. And there are some specific bit on which Arista wanted to pass on as the as a part of the specs. So if I see that how the spec and mask in this case are going to look like, so if you see, we have first destination IP address, again we pass it as it is, and then we have source IP address, then we have vendor specific protocol, and then we have timestamp, and these are something specific to this particular use case. And then we have the changing L2 timestamps value. And because we wanted to hash on the basis of these changing L2 timestamp value, so our mask were like we actually masked those L2 timestamps value. And like I said, this is very specific to like Arista case, but using the same methodology, we can actually calculate the specs and the mask for any other use case also, and we can just pass it into the raw pattern like when we are configuring our flows, and we will be able to achieve we will be able to classify our flows on the basis of that. And like whenever we talk to the different customer, when they use this raw pattern mask, or maybe when they are calculating this spec and mask, they always get overwhelmed that how this specs and mask can get calculated, because sometimes it is tricky to calculate these specs and mask. And for that we actually have, first of all, before I go into that particular tool, so this is how your test PMD command is going to look like. So if you see, like what Adam and Lucas just shared, that in their example, it was mainly flow create 0 ingress pattern, and then it was the what are the pattern they want to match on. But in this case, it is just in this case we actually now have raw pattern, and then it is followed by the spec and the mask which we actually calculated above. So this is now how your command is going to look like in the test PMD side. And the thing which I was mentioning, that sometimes a user gets overwhelmed about how to calculate this spec and mask for their particular use case. And in that case, there is a tool which is available called as Packet Forge. It is like open source. So in that case, you can just provide your rule, and it will actually helps to calculate your specs and mask. So like if you are needing some help that okay how to calculate this, you can use this. I've actually included the link of that in the slide, so if anyone is looking to use that particular tool, they can. And also this whole presentation is actually based on the white paper which we have initially recently released in collaboration with the Arista. So if any one of you is looking for more information around that, okay, like why Arista was doing the time, hashing on the basis of the L2 timestamps, or if you want to, if you are looking for more information on any of these functions, that okay, how RT flow create or how RT flow API is working. So it is actually there in the, so I've included that link of that white paper also in this at the end of the presentation. So feel free to check it out. So you will get more information around any of the topic here. So yep. So these are the references. Like I said, it has packet forged link. It also has the link of the the white paper, which I was just talking about, and also it has the DPDK. I think so. Yeah, it is one one more document which can which also have can help a user to having more understanding around the specs and mask and how the whole raw pattern is being calculated. This is a second paper which can help you guys. So, yep. So that's all from my presentation actually. So, if you have any question, please let me know.
Is the code public?
Sorry?
Is the code, I mean, is it in the, it's that
yeah, so
RT flow, sorry. It's on, right? Okay. Is the RT flow, generic RT flow action, sorry, match and action, is code available now?
yeah, so it's in the DPDK. So in the like I said, it is in the DPDK. So there is one particular in the DPDK raw pattern, that particular feature. So when you are setting your flows or configuring your flows,
okay,
you can use that. Yeah,
the source code is available.
Yeah, it is available.
And this tool to JSON file, so that's also not available as well.
Yeah, it is available. It's open source. It's
so
available.
How deep we can go in the packet?
Sorry?
How deep?
How deep that particular tool can go into the packet, or
No, I mean mask. I mean the mask length.
Mask length. I don't remember straightforward. Tim, do you remember how deep up to how deep we can go into the packet actually?
So that depends upon the particular parser and the particular NIC you're working with. But I will say it's more in the order of, say, hundreds of bytes typically, rather than thousands of bytes. So it just depends upon which particular adapter you're learning on. And
then how about number of rules you can scale?
So I think so number of rule, it will depend upon your how much your hardware can support.
That's true too. I mean, as a general rule, say for the 800 series NICs, it's on the scale of say thousands of rules. But again, it depends upon the particular adapter you're learning on. And the complexity of the rules too.
Hi, Shobin. Thank you. Lucas here. I wanted to ask, but I think you answered it with the previous question, if it's supported on regular E810 NICs. That's great. When I was evaluating the pattern matching for Suricata, and I also basically looked at the raw action in RT flow as a, let's say, inline pattern matching opportunity there. It almost fitted my requirements. It just didn't support the case insensitivity, which, I mean, this whole idea about the raw pattern wasn't probably developed with the idea of pattern matching, but I think it could be a side use case as well. Does the current support also of the row pattern the other subfields like the offsets and depth that are kind of specified in the documentation?
In the white paper?
No, in the implementation. Does the implementation support because the spec what you had also allows to specify how deep the pattern should be located, or at which offset it should start searching for the pattern or for the bytes. So I was just wondering if it's already also supported in the current Intel implementation.
I think so. I can check for you and come back to you with that. Tim, do you know about this actually?
Well, to say if I kind of understand the question correctly, if you're talking about things like VLAN headers and so forth, if you are configuring the NIC to strip those things out, certainly that would help in this case. You don't have to worry about the offsets in particular. Other things like MPLS labels can also be accounted for. But I mean, if there's anything particular that does require a particular offset, like Shobi mentioned, we can follow up there.
Okay. And is there any chance that the current implementation will support the byte matching on whole packets and not just the first 100 bytes?
I think so. In that case, you can mask them out, whatever you are looking to match on. So you can actually mask them out with the help of the mask.
Yeah, but I think you still mentioned that the search only goes for the first 100 bytes, or maybe Tim mentioned that
yeah.
It's in the order of 100 bytes and not in order of thousands. So packets can be 1,500 bytes long in general. So I would kind of like to match on the whole packet. So I was wondering if this can be supported in hardware.
I think so. Like Tim said, currently only the 100 byte is it can go up to the 100 byte, but yeah, it won't be like you said. You want to match if you want to match the whole packet, then you need, in that case, you need to select a certain bit with up to the 100 bytes only. Yeah.
Okay, thank you.
Yeah, I was going to add there, I mean, we're still limited by the parser itself. Yes, I mean, whatever that restriction is on how many fields we can go into the packets. I mean, in general, we're not going to be able to get to, say, like the HTTP layer right to the packet. We're still going to be bound there by the hardware.
Also,
sorry, can he use the mic?
No, I'm just thinking about it slightly differently here. Like, I don't know. There are solutions we developed where we have a chain of mask or matching rules, and then each action is also a matching for the next. So it's a chain of things. And the back end, we do not have a hardware. We have a software implementation, right? Which is very simple, like drop a packet, or do something else, right? But the whole thing is about the hash lookup of all this chain of matching of different masks, different offsets, right? So do you support this chain of rules, rule match and actions?
I think so. Yes, Tim?
I was going to say we can follow up there again, but I mean, there are still some limitations there, but I mean, you can certainly change certain combinations together.
Yeah. Yeah.
Hi. Do you support the flow for VFs on the 810 NIC as well, or is it only on the PF?
I think so. It's supported on both VF and PF. Am I right, Tim? Sorry, because Tim is like a technical lead for this, so I.
Correct, sure, but yeah, it's both the IVF driver, the VF, and the PF in this case.
It is supported.
Yeah, on so IAVF and on the PF side as well. So
Okay, okay. Because the last time I tried on a 5.15 kernel, the ICE driver didn't have support for it. Maybe it's added recently. Or
Yeah, maybe you can give it a try. If you have any problem, reach out. Maybe we will be able to help.
I already had a problem. That's why I was asking. Thanks.
Okay, I think we can close. Thank you.
Yeah, thank you so much, everyone.
Thank you.
Okay, so hello everyone. My name is Dariusz Sosnowski, and today I wanted to talk to you about flexible parsing in Flow API. And this presentation was co-authored with Ronnie Marianai, also from NVIDIA. So in this presentation, we'll basically be tackling similar problems as Shobi and Tim mentioned. So first, I'm going to walk through specifically how packet matching is defined and how applications use Flow API to define packet matches on the hardware offloaded rules. Then we'll talk a bit about custom protocol matching and what would be needed from Flow API to allow applications to add custom protocols in the Flow API. And afterwards, we'll discuss the flex flow item, which is part of the Flow API, which aims to provide applications ability to define these custom protocols. At the end, we'll also talk a bit about requirements of packet patterns, flow patterns in the Flow API, and how we can maybe reduce them to allow a better architecture of the hardware offload. So first, a very brief intro to the Flow API after already 2 presentations on matching. So basically, in the Flow API, it gives DPDK users an ability to program custom behavior in the NIC so that the CPU is offloaded from some tasks. The basic concept in the Flow API is a flow rule, which consists of main 2 components. A pattern, which defines which packets we want to work on, and actions, which defines what to do with the packets, matching the given pattern. In DPDK, this API is available in both synchronous and asynchronous version. The asynchronous version is called the template API. So let's focus on the packet matching itself. So the main building block in the Flow API to build our description of the packets we want to work on is the RT-flow item. RT-flow item has a type, which basically defines whether this will be described Ethernet header, IPv4 header, IPv6 header, etc. It has a spec, which is a pointer to the header struct containing the values we want to match on, like the specific values, whether for example, the addresses or ports in layer 4. We have the mask, which defines which bits of the header we want to match on, so that basically the hardware will only look at those and the rest will be disregarded during the matching. And we also have a last, which defines basically the end range. If we wanted, for example, to match on a range of IP addresses, then spec and the last will define from which address to which address will match. And we can take a look at more complex examples. So when we have the RT flow item itself, then the whole pattern is built as an array of flow items. In this example, we have an Ethernet, IPv4, UDP, and VXLAN pattern. So each item specifically defines through spec and mask the values we expect in this layer. For example, Ethernet item defines in the Ethernet header what kind of destination MAC address we want. IPv4 item defines the destination IPv4 address, and the VXLAN header can define the expected VNI value in the VXLAN header. As you can see in the Flow API, there is an expectation requirement that the pattern itself resembles the structure of the packet. So like the items are ordered as it resembles the structure of the packet headers in the packet themselves. There is also some implicit assumptions. So for example, if IPv4 header, IPv4 item follows an Ethernet item, then it means that the driver has to configure an implicit match on the ether type so that we only match on the IPv4 packets. And the same happens for UDP, where we match next proto value in the IPv4 header. And for example, in VXLAN, this kind of implicitly forces the destination port to be implicitly matched to the specific value. But what if we wanted to support custom protocols matching? Different use cases might require either matching on protocols which are not yet added to Flow API, or match proprietary protocols which cannot be fully upstream or open sourced. In other systems, other APIs such as P4, where we'll go over the example, we can define our own parser from scratch. So in P4 language, there is no built-in definition of how even standard network headers look like, and developers define them from scratch. So for example, here we define our structure of the Ethernet header, in this case without any VLANs, and the parser is defined as a kind of a state machine. So we start from the start of the packet, we assume that all the packets are Ethernet, and we go to the parse Ethernet state. In this parse Ethernet state, we assume that whatever bits we got in the packet are Ethernet header, and we extract the value of ether type, and based on that we go to the next stage of the parser. In this example, we either go to IPv4 or IPv6 parsing stage based on the ether type value. If we, for example, go here to the IPv4 parsing stage, then as we all know, the IPv4 is a dynamic length header. The minimum length of the header is I believe 20 bytes, if I recall correctly, but we can have many IPv4 options. In P4, for example, we do not have to parse the whole packet header. We can only look at the parts we are interested in and the rest skip. In this example, when we reach the parse IPv4 state, we extract the basic IPv4 header, and then based on the header length field in the IP header, we either go directly to the protocol dispatch state in this example, which based on the protocol value will continue, or go through an intermediate step, which will, based on the header length field in the IP header, will skip the unnecessary bits for us and will continue from there. So in this case, the question is, what kind of building blocks are needed in Flow API to achieve similar customizability as we have in P4? There are 4 main building blocks. So first, we need to know how to recognize the size of the new header. Our custom protocol can be either a fixed size header, or the header size can be defined based on values stored in some field. This will allow our parser, this will allow Flow API and the driver to configure the NIC to know how many bits to skip when parsing this header. The second building block is we need to notify the hardware which bits of the header are really interesting to us, which bits we want to look at, which bits we want to match on, and which bits we want to modify. Let's say that for our custom IP, we only want to look at the addresses. The rest can be ignored, for example. The third building block is how to recognize what comes after our custom protocol. if we, for example, wanted to define a custom tunneling protocol, we need to know how to recognize what it follows. Basically, whether we encapsulate IPv4, IPv6, or raw layer 2 frames. And the last building block required is how to connect our new custom header to the existing ones. Let's say that we want to create a new layer 4 protocol. How do we recognize it in normal IPv4? It's important to note at this step that as in P4, where everything was defined from scratch, it's not needed in Flow API that everything is defined using these building blocks. With these building blocks, the custom protocol could be attached to the existing hardware parser, so that we can only add a new protocol, connect it with IP, IPv4, IPv6, the standard versions, and connect them with other standard protocols, for example, for tunneling. And these building blocks are provided by the Flex Item API. This is available from DPDK 2111. As of now, it's implemented only by MLX5 PMD. And basically, it exposes these building blocks so that now application users can create their own custom protocols and apply matches using these new Flex items, or even modify these custom headers through the Flex item. How the usage of this API goes on the high level. So first, we need to define a new item. There is a struct called rtflow flex item conf, which defines all these building blocks described previously. Then we register the new flex item in the driver. As part of this API, the driver configures the hardware, notifying it of reconfiguring the hardware parser so that it knows about this new custom header. And then we want to match or modify. We use either flex item type in the rtflow item or field flex in the modify field action. So let's go step by step through the definition of the building blocks in this API. So first we need to define the header format and the header length. So it's critical for the hardware to know whether our new header is outer header, inner header, or a tunnel header. Or it can be both outer and inner. This information is required because depending on the type of custom header we want to introduce, a different number of hardware resources might be utilized. So for example, here I use the standard header as examples of how they could be defined in the Flex API. So for example, here we have UDP header, which is defined as mode multi, which means that it can be outer, it can be either outer or an inner header, or IPv4 header, which can be the same way. We also have VXLAN here, which obviously can be only a tunnel header here. But then knowing how this header can be must be interpreted on the stack of packet headers, now we need to know its length. And through the Flex API, we can define whether it's fixed, as for example with UDP and VXLAN, they are fixed length, and based on some field value. And Flex Item API provides an ability for the user to define the length of a header as some static value plus value of the field shifted by some bits. In case of IPv4, we use as the base header value 0, and we basically specify using bit offsets the location of the IHL field, the internet header length. We tell that it's 4 bits of size, and then we need to shift this value by 5, basically implementing the logic defined in the IPv4 header. Okay, so now we know what is our header used for, how long it is. Now we need to recognize, okay, when we parse it, how to jump from this custom header to next headers. For example, the encapsulated headers. This is defined through the next protocol field. There is one issue in the slides to be fixed later. But basically, we need to define where in the packet the hardware should look at to determine the subsequent header. So using the standard examples, so for UDP, there would be a field at 16-bit offset taking 16 bits, it would be our destination port. This would allow us to decide what protocol follows UDP. For IPv4, we're basically using the same bit offsets and sizes, point to the next protocol field. Now, since through the API we'll tell the driver, okay, look at these bits in the custom header to determine the next parser, the next stage. Now we need to connect them to the existing parser stages in the hardware. This is achieved through configuring output links in the Flex item API. And in this case, for example, this uses standard RTFlow item types to define what type of protocols will follow our custom header. And in this example, we specify that if, let's say, we define IPv4 header, then we can have that it can be either TCP if now our next header value is IP proto TCP, or it can be UDP if the value is IPv proto UDP. Now for the last building block, so now we have second to last building block. Now we need to take our custom header and connect it to existing parser stages in the hardware, so that the hardware knows that when we see specific, for example, UDP destination port or ether type or IP protocol value, we need to start parsing our custom header. This is defined through input links in the API, and basically each link is an RTFlow item using the predefined types in the API. In this example, for example, IPv4 or IPv6. And through spec and mask, we define the header values we need to match on. And from these values, the custom header parsing must start. And as a last step, we need to tell the driver through this API which fields are we really interested in looking at. This is called sampled fields. And we basically, in this API, provide a list of fields specified by bit offset and the bit size. In this example, if we define as custom TCP header, and let's say that we're only interested in the source port, destination port, and TCP flags, we provide 3 sampled fields, each with specific offsets and sizes of the fields we are interested in. These sampled fields will basically determine for API users which values we can match on and which values we can modify. And now if you want to match using this flex item, right, we basically use the standard RTFlow item struct with the type of flex and provide the handle to the already registered flex item. So after we configured the flex item using the building blocks, we register it in the driver, hardware is configured, we receive a handle. This handle is used in the spec and mask of the RTFlow items, and we provide in the API we provide an arbitrary byte array which defines which bits of the header we want to match on, which must resemble like the samples we provided as well. In this case, since we were using the standard protocols, we can reuse the TCP header struct defined in the DPDK API, but this can be any arbitrary byte array. And the similar thing is also for packet modification. So there is an action called modify field, which is a generic single flow action, which can be used to either modify a packet or a copy value from one packet header to another, or from between fields in the same header. And in here, when we use this action, we can also use as a destination or source, we can use the flex item with the provided flex handle. In order to copy a very specific part of our custom header, we specify the bit offset, the same as in the similar manner as in definition of the flex item. So now going a bit on the tangent. So okay, we have in the Flow API ability to add new custom protocols, and we can define basically the whole header structure in the Flow API. But what if we wanted to reduce them? Because as I mentioned, the Flow API requires a pattern, the array of RTFlow items, to represent the whole header stack. If I want to match on VXLAN packets and I want to look at both outer and inner header values, I need to define Ethernet IPv4 UDP VXLAN, then again Ethernet IPv4 UDP, and so on. This can cause several issues. For example, this makes the matching specification longer, which increases hardware resource usage. We might need more memory to store such rules. And it also requires more software computation. Basically, whenever I need to add a rule, I need to provide all the headers again and again. And also, in many cases, this is unneeded because, for example, I only care about inner headers. I don't care whether it's VXLAN or VXLAN in IPv4 or VXLAN in IPv6. I only care about the inner headers. I don't want to provide and I don't want to match on the outer headers themselves. It would be easier if it would be allowed on the API level that I can split the matching in phases. That in phase 1 I match the specific tunnel, which I allow, and the second phase I match on the inner header contents. This is allowed in relaxed matching. This is part of the Flow template API, so the asynchronous version. And basically, in the template API, I can provide the pattern template, which describes what I want to match on. And by specifying that this pattern template is relaxed, I lift the requirements as in normal flow API. So there are no ordering there is no assumed ordering limitations, and most importantly, there are no implicit matching limitations. As I described previously, when I put IPv4 item after ETH, there is an assumed match on ether type. With relaxed matching, there is no such thing. And in this would allow basically the splitting in stages. So for example, now in some very small set of rules, I can match that, hey, I want VXLAN with IPv4 UDP protocols on the outer headers, or with IPv6, or even totally unrelated tunneling protocols such as GRE. I can match my required tunnel headers in the first stage, and then in the second stage, I can omit the outer headers and just match on the inner ones and the fields of which I only care about. In this example, VXLAN is used without any match. It's kind of an indicator to the driver that the items following that are inner, because RTFlow items themselves do not have any kind of way to specify that it's outer or inner. It all depends on the order. So this VXLAN is used as kind of a marker. This kind of design and this kind of relaxation of the requirements provides two main benefits. First, we can reduce the rules length on the rules which matter for us. We can imagine that these inner header matching rules are in a very high scale flow tables, like a few million flow rules. By reducing the rules length, we can fit more of them. We can lower the hardware resource usage and also improve the flow offload on the software side. We only need to provide the data we really need. We don't need all of the other items to, we do not need to fill other items to just fill in the requirements of the API. And it also enables table unification, which improves it simplifies the design a bit, because right now you can notice that it doesn't matter for me when matching inner headers whether the outer header was IPv4, IPv6, VXLAN or GRE. In this example, I only care that, hey, I want to match tunnel to traffic. I don't care about the tunnel itself. So what I do is in the phase 1 I match the accepted tunnels and then don't care about the specific tunnel at all. Which brings to one point, as you may have noticed, I used VXLAN as an indicator of that, hey, the following items will be inner headers. One improvement we can do in this whole approach is to introduce the generic tunnel item, which would not be used to match specifically all the possible tunnels supported by the hardware, but in relaxed matching would serve as an indicator of hey, the subsequent items will be inner headers. But this is something for possibly discussion after the talk. Thank you very much.
You mentioned that this is only supported in MLX5, right?
Right, yes.
Are you aware of any plans to support it in other PMDs or whatever?
I don't know of any plans. Yeah, it's basically a question to the whole community.
Yeah.
I would love that the Flex Item API or Flex Marching or even the template API itself, which is only supported MLX5, it would be great to see adoption of these APIs in other NICs. As we have seen, like there are capabilities to match custom protocols. It's up to discussion. Okay.
No more questions? Thank you.
Thank you.
Southern, I know a lot of you, not all of you. I'm the senior program coordinator at Linux Foundation assigned to DPDK, and I've been on the project for 3 years. I'm also on LFAI and data and the Open Insurance Data Link project. And I'm approaching it, I've said this before, when I just got up to say a few words at different summits. This is my 4th. I have kind of a unique perspective here, and then I think I'm probably the only person in this room that is not a hardcore tech person. I'm communications management, stakeholder management. So in full disclosure, I understand about 2% of what is said here. And I approach it from a different angle, and so it gives me a unique kind of perspective and take on things. And one of the things that I always notice in every summit, and I say this every year, is that we're really about community. It's great to see the same people year over year. It's a testament. I've gotten to know, a number of you, and it's a testament to just the loyalty that our community has to the project. And it's reflected not only on an interpersonal level, but also on a membership level. I think we set some kind of, I probably shouldn't say this on the record, but I think we unofficially set some kind of record at Linux Foundation for having the most membership retention, 100%, I think 4 or 5 years in a row now. The last one that member that we lost was in 2021, and that's almost unheard of. And again, it's just a reflection on the strength of the community on a corporate level and how loyal our members are to us, and that's great to see. And also the strength of the platform by extension. Our conferences are pretty modestly scaled vis-a-vis larger LF events, and this project has sort of a smaller leadership than, much smaller than something like CNCF, but our community members feel very, very strongly about the project and are very invested in it. And are really committed on a tech board level and a governing board level to expanding and innovating in different directions. And that's the other thing that I hear. Ben Thomas, who's not here, but who will be at our summit in September, I referenced last night in our private tech board governing board meeting the term one-trick pony. And that's because that was his perception kind of coming into the project. You guys do one thing, you do it over and over again. And then after he came out of Montreal, he just said, holy cow, there's all kinds of innovation going on in this project. It's being expanded and used in all kinds of different interesting ways. We have one stakeholder who's using it in the astronomy telescope. I could go on. And I think these conferences are a great window into that. That kind of innovation, and that's what I always look forward to at the summits. So there's that. And along those lines, I might want to ask, I think Tim and Ian, the chair and vice chair, would agree with me on this, just is that you, as community members, communicate with our tech board and governing board members on Slack, via email, as far as what innovations you want to see. Because it is not always easy for us to get a window into that other than just one-on-one conversations that we have now and then. So if you want to see us evolve in a certain direction, let us know. I can't make any promises on behalf of the project, but other than just the fact that we will discuss it internally, gauge the feasibility of it, and then take steps accordingly as we're able to. A couple of logistical matters as well. We're rolling out, Tim mentioned earlier this morning that we're working to bring revenue, spending in line with revenue. So that's not a secret at all. The project has been very strong financial position for several years now. We have been cutting into our revenue and our buffer a bit, and so we want to start to. Not that there are any, not that this is more of a precaution than anything else. We don't really see any warning signs at this point, but we do feel like it makes sense to be a little more fiscally conservative in terms of spending. So we are going to start to roll back to community-run events. Just waiting in a little bit at first, but we have the first one this September, as mentioned, is September 17th to 18th, and our member Intel is hosting that at their campus on Mission Boulevard in Santa Clara. And again, it is, at least since I've been at the project for the last 3 years, we've not done that. So it's a bit of an experiment for us. Certainly haven't done it since before COVID. And Intel has been just very gracious in terms of facilities, security, AV. It is costing the project, but it's costing us less than it would with the way that we did this event and other events. And LF, Linux Foundation VM Management Services, does a fantastic job. So it is not in any way a reflection on them. But, you know, Evie and Bridget and their team are just sensational. But as a rule, they are geared toward bigger projects and bigger events. They handle CNCF, they handle, you know, different LF Edge and so forth. And we are a bit of a smaller community. So it is a way for us to at least try to scale back in terms of cost. We're really excited about that Santa Clara event too. You can find we have the code up there. You can QR code, so you can register. You can submit to the CFP for talks there, and we think that it's a really great, fertile area to start in geographically, just from the standpoint of being right in the middle of Silicon Valley. So that's going to it's going to be a bit of a different orientation than our doing one in Europe. And we have great faith in terms of how that's going to turn out. So far, everything's going smoothly. We're on CVent as a registration platform and sessionized for the CFP. A couple of other logistical matters. We have a cocktail, food and cocktail reception tonight. I'm going to butcher this name. His Czech name, Peter Vargisuda. We meet in the lobby. We're going to meet in the lobby at 5:45 this evening and walk over together. So you're all invited to that, and I'd like to encourage you to attend. Great opportunity to socialize as well and continue to get to know members of the community. And finally, Evie and Bridget have suggested, I think it's a great idea, we tried to do a group photo at every summit. So we're going to gather just as soon as I finish. If you all want to just gather on the stairs, and we're going to take a photograph just to put up on the website. We'll do that momentarily. So thank you all. It was really, it's great to see all of you, and we'll look forward to the reception in a few minutes. Thank you.